It should have been a simple test. The wormhole, a shimmering, stable tear in the fabric of space-time, stretched from a quiet orbit around the Moon to a designated empty patch of space near the orbit of Neptune. A welcome party was already in position there, waiting to greet the brave crew who would be the first humans to take a shortcut through the cosmos. The effort to reach this point had been monumental. A multi-generational project that had consumed a significant portion of humanity's resources and scientific talent. It had required us to reach down into the roiling, chaotic sea of the quantum foam, that submicroscopic realm where space-time itself is in a constant state of turmoil, and to pluck a single, nascent wormhole from its depths, carefully nurturing and expanding it to a macroscopic, traversable size. The equations of Einstein's general theory of relativity had predicted the possibility of such structures, these space-time bridges, for centuries. And now, after decades of painstaking work, here it was, a shimmering, spherical gateway to the stars. This was not just a scientific experiment. It was the culmination of a dream, the dream of interstellar travel, of a future where humanity was no longer confined to its cradle, but could finally step out into the vast cosmic ocean. The last calibrations were made, the final checks completed. The ship, a sleek silver vessel named the Pilgrim, and its four-person crew, entered the wormhole's throat, passing easily through the spherical, shimmering boundary of its entrance. From the observation posts on the Moon, onlookers watched as the ship receded, its form gradually shrinking, appearing to move effortlessly and serenely towards its destination, some 4.12 billion kilometers away. At the other end, near Neptune, the reception party watched on their own screens as the ship began to appear, a small point of light that grew steadily larger as the minutes ticked by. A preliminary unmanned test probe had taken just over 30 minutes to traverse the distance, and the Pilgrim seemed to be on a similar, perfect trajectory. A quiet sense of triumph, of a new era dawning, began to settle in. But then, a subtle shift in the data, a flicker of concern in the mission control centers on both ends of the journey. The ship, which had been steadily growing larger in the viewports of the Neptune reception party, appeared to slow down. Then, it seemed to stall, its image frozen, hanging in the void just beyond the wormhole's exit. 30 minutes passed, the expected arrival time. The ship did not emerge. An hour passed, then a day, then weeks, then months, then years. Time-sensitive, high-precision telescopes, positioned at both the entrance and the exit of the wormhole, were able to confirm that the ship was, in fact, still in motion, but its progress was almost imperceptibly, agonizingly slow. A new and terrifying reality began to dawn. The crew of the Pilgrim was trapped, not in space, but in a strange, distorted, and seemingly endless river of time within the wormhole itself. A frantic and desperate debate raged across the solar system. Should we send a rescue mission? But how could another ship enter the same treacherous passage? Should we try to turn off the massive generators that were feeding the exotic, negative energy required to keep the wormhole stable? But any sudden change to the delicate balance of forces could cause the wormhole to collapse catastrophically, tearing the ship and its crew to pieces. Every option seemed to lead to the same tragic conclusion. The only safe option, the only humane option, was to wait. And so, humanity waited. We watched the frozen image of the ship, a silent monument to our ambition and our hubris, and we waited. 500 years passed before what was left of the Pilgrim finally, slowly, drifted out of the wormhole's exit. It was a ghost ship, a broken, pitted husk, its systems barely functioning, its hull scarred by centuries of exposure to the harsh, and still not fully understood. Conditions within the wormhole's throat. The crew, of course, was long dead. Their skeletal remains still strapped into their command chairs, a silent, eternal testament to a dream that had turned into a nightmare. Only then, after the last of the wreckage had been recovered, was the wormhole finally and permanently shut down. We had miscalculated. The beautiful, elegant equations of general relativity, the machine that had promised us the stars, were not enough. We thought we had understood the complex and treacherous intersection of gravity and quantum mechanics. We thought we had accounted for every possible interaction, every subtle nuance of the physics, but some crucial hidden variable, had been missed. Humanity looked out at the distant, glittering stars, and we had never felt more profoundly and more completely alone. The universe had offered us a shortcut, a beautiful and tantalizing promise, and it had turned out to be a trap. The story of wormholes is a story of the power and the peril of a great scientific theory. They are a natural and almost unavoidable consequence of the mathematics of Einstein's general theory of relativity. The idea of them is almost as old as the theory itself, but relativity, for all its beauty and its power, is just a machine. It is a set of rules, a mathematical algorithm. You feed it an input, a particular arrangement of matter and energy, and it gives you an output, a prediction for how space-time will curve, and how matter will move within that curved space-time. The machine does not, and cannot, tell you whether your initial input, your imagined scenario, is something that the universe actually allows. It is up to us, as physicists and as observers of nature, to figure out which of the many possible solutions to Einstein's equations correspond to the real world, and which are mere mathematical fantasies. The story of our ill-fated test pilots is a cautionary tale, a reminder that the path from a beautiful mathematical idea to a physical reality is often a long and treacherous one. So, what would it really take to build a wormhole? What are the physical mechanisms that might allow for their existence, and what are the deep and perhaps insurmountable obstacles that might forbid them? Are they a viable, if distant, hope for our future among the stars, a destination for our dreams? Or are they, as our fictional story suggests, a beautiful but deadly siren's call, a path that leads not to a new world, but to an early and very lonely death? The answers to these questions lie at the very frontiers of our understanding of gravity, of space-time, and of the fundamental nature of reality itself. In the year 1848, just 1 year before his own mysterious and untimely death, the American writer Edgar Allan Poe published a strange and sprawling work of prose that he considered to be his masterpiece. Its title was Eureka. The text is a dense and often confusing mixture of poetry, philosophy, and speculative cosmology, and it is largely ignored today, overshadowed by his more famous and accessible tales of horror and mystery. But buried within this tangled mass of prose, about 2/3 of the way through, in the midst of a rambling discourse on the nature of interstellar space, Poe makes a startling and uncannily prescient declaration. He states, almost as an aside, that space and duration are one. In Poe's poetic and intuitive vision, the 3 dimensions of space and the single dimension of time were not separate entities, but were somehow unified, 2 aspects of a single underlying reality. Nearly a century later, a young physicist named Albert Einstein, working in a patent office in Bern, Switzerland, had no idea that he was, in a sense, echoing the strange and beautiful intuition of a long-dead New England poet. The year was 1905, a year that would go down in the annals of science as Einstein's Annus Mirabilis, his year of miracles. In that single, remarkable year, he published a series of papers that would revolutionize our understanding of the physical world. And in one of those papers, perhaps his most consequential, he formulated his special theory of relativity. This theory was built on two simple, but radical, postulates that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is a universal constant, the same for all observers, regardless of their own motion. The consequences of these two simple ideas were profound. They showed that measurements of length and time are not absolute, but are relative to the observer. A moving clock ticks more slowly than a stationary one. A moving object appears shorter in its direction of motion. Space and time were no longer the fixed, absolute, and independent entities of Newtonian physics. They were dynamic and intertwined. But it was Einstein's former teacher, the mathematician Hermann Minkowski, who took the final, crucial step. He realized that the strange, counterintuitive effects of special relativity could be understood in a much more natural and elegant way if one abandoned the idea of a three-dimensional space and a separate, one-dimensional time, and instead worked with a single, unified, four-dimensional entity space-time. In Minkowski's geometric formulation, space and time were not identical, as Poe had perhaps imagined, but were different facets of a single, unified reality, two inseparable components of a four-dimensional continuum. Einstein, learning once again from his old teacher, quickly embraced this powerful new idea and used it as the foundation for his next, and even greater, leap of imagination. In 1915, he unleashed upon an unsuspecting world his general theory of relativity. In the new and beautiful language of general relativity, space-time is no longer a passive, static stage upon which the drama of physics unfolds. It is an active participant in the drama. The presence of matter and energy causes the unified fabric of space-time to bend and warp. And in turn, the curvature of space-time tells matter and energy how to move. The great physicist John Archibald Wheeler would later summarize this profound and beautiful idea in a single, elegant phrase. Space-time tells matter how to move. Matter tells space-time how to curve. This is not an abstract, theoretical concept. It is a physical reality that is happening all around you and within you at this very moment. The Earth is not held in its orbit by a mysterious, invisible force of gravity reaching out from the Sun. It is simply following the straightest possible path through the curved space-time created by the Sun's immense mass. The light from distant stars is bent as it passes by a massive galaxy, a phenomenon known as gravitational lensing, which allows us to use these galaxies as natural cosmic telescopes, and as massive, cataclysmic events, like the collision of two black holes, unfold in the distant universe. They send out ripples in the fabric of space-time, gravitational waves that travel across the cosmos at the speed of light. As these waves wash over the Earth, they are constantly, gently stretching and squeezing the very space you are in. The effect is impossibly small, a distortion on the scale of a single atomic nucleus, but it is real. And with our incredibly sensitive gravitational wave detectors, we can now hear the faint, cosmic symphony of these distant, violent events. But the general theory of relativity, like the writings of Poe, is a work of immense beauty, profound depth, and sometimes daunting complexity. It is more than just a simple physical theory of nature. It is a machine. It is a set of 10 tangled, nonlinear, four-dimensional differential equations. You provide the machine with an input, a specific, imagined arrangement of matter and energy, and the machine, after a great deal of mathematical wrangling, will give you an output, a precise, mathematical description of the resulting geometry of space-time, and a prediction for how that system will evolve. But the machine is agnostic. It does not tell you whether your initial input is a scenario that is physically possible in our universe. That is a question that you, as a physicist, must decide. This is not a feature unique to relativity. Newton's law of universal gravitation, which relativity replaced, works in the same way. You can, in principle, use Newton's law to calculate the gravitational field of a solid iron rod that is 10,000 light-years long. The equations will dutifully give you an answer. But it is up to you to use your knowledge of the rest of physics, of astrophysics, of material science, to decide whether a 10,000 light-year long solid iron rod is a physically plausible object. The problem is that the equations of general relativity are vastly more complex, and their solutions often describe phenomena that are far outside the realm of our everyday experience, making it much more difficult to use our intuition to separate the physically real from the mathematically possible. The physics community in the early 20th century recognized the profound truth and beauty of Einstein's theory, but its sheer mathematical difficulty was so great that many preferred to work on the more tractable problems of the burgeoning fields of subatomic and astrophysical physics. The pioneering physicist J.J. Thomson once famously remarked, "I have to confess that no one has succeeded in stating in clear language what the theory of Einstein's really is." Despite this daunting complexity, some progress was made in the years immediately following 1915. While serving in the German army on the Russian front during the First World War, the physicist Karl Schwarzschild found the first exact, non-trivial solution to Einstein's equations. He took the machine of relativity and fed it the simplest possible, non-empty input, a single, static, spherically symmetric, non-rotating mass, a mathematical object intended to approximate the gravitational field of a star, like our sun. The machine dutifully churned out an answer, a description of the curved space-time surrounding this mass. The Schwarzschild metric, as it is now known, was a triumph. It accurately described the orbits of the planets in our solar system, and it made new testable predictions, like the bending of starlight, which were later confirmed with stunning precision. But buried deep within Schwarzschild's elegant equations, there was a strange and disturbing feature, a mathematical pathology that seemed to suggest a reality far more bizarre than anything in our solar system. The solution contained a singularity. The equations predicted that if the entire mass of the object were to be squeezed below a certain critical radius, the Schwarzschild radius, then the curvature of spacetime would become infinite at the center, the object's own. Immense gravity would overcome all other forces, and it would collapse into a single, dimensionless point of infinite density. This singularity would be surrounded by a one-way membrane, an event horizon, a point of no return from which nothing, not even light, could escape. The machine of relativity had produced a monster, and now it was up to the physicists to decide if this monster could be real. For decades, the overwhelming consensus was that it could not. Most physicists, including Einstein himself, scoffed at the idea. They believed that the singularity was just a mathematical artifact of the oversimplified, idealized scenario that Schwarzschild had used. In a real physical collapse, they argued, the complex, messy physics of a real star, its rotation, its pressure, its radiation would surely intervene and prevent the formation of such an absurd, infinitely dense point. In a 1939 paper, Einstein himself argued that no real object could ever be compressed to its Schwarzschild radius, that the forces of nature would always win out over the pull of gravity. These hypothetical objects, which were then known as frozen stars, were, in his view, a physical impossibility. But a young American physicist named J. Robert Oppenheimer disagreed, just a few months after Einstein's dismissive paper. Oppenheimer, working with his student Hartland Snyder, was exploring the fate of massive stars. He had just completed a groundbreaking calculation that determined the maximum possible mass of a neutron star, the incredibly dense remnant left behind after a supernova explosion. He then asked a simple but profound question: what happens to a star that is more massive than this limit? What happens when a star is so massive that not even the immense quantum mechanical pressure of densely packed neutrons can hold it up against the relentless crush of its own gravity? Oppenheimer and Snyder took the full known physics of a massive star and fed it into the machine of general relativity. And the answer that came out was the exact opposite of Einstein's. They found that for a sufficiently massive star, there was nothing, absolutely nothing, that could halt the process of gravitational collapse. The star was doomed, and once the collapse began, the machine of relativity told them exactly what would happen. In their landmark paper, they stated their conclusion with a chilling clarity. The star thus tends to close itself off from any communication with a distant observer. Only its gravitational field persists. They had, for the first time, provided a physically realistic mechanism for the formation of a black hole, but their work was published on September 1st, 1939. The very same day that Germany invaded Poland and the Second World War began. The world's attention was, understandably, focused elsewhere. Their paper was largely forgotten for decades. Oppenheimer himself was soon swept up into the immense, world-changing vortex of the Manhattan Project. His brilliant mind diverted from the mysteries of the cosmos to the terrible, practical physics of the atomic bomb. He would never return to the astrophysical questions that had so fascinated him as a young man. But history and the universe would eventually vindicate his and Snyder's conclusion. In the decades that followed, through a combination of theoretical advances and new, powerful astronomical observations, it would become indisputable. Black holes were not just a mathematical curiosity of Einstein's equations. They were real, physical objects scattered throughout our universe. The machine of relativity had, once again, been proven right. But was this all that the machine predicted, or were there other, even stranger, monsters lurking in the tangled depths of its equations as Oppenheimer was working away in the deserts of New Mexico? Another brilliant mind, working in the very different, and often perilous, environment of the Soviet Union, had found another, even more bizarre, possibility. He had found the black hole's mirror twin. The Soviet astronomer Igor Novikov was born in Moscow in 1935, and despite the immense challenges of working as a scientist under a politically repressive regime, he quickly rose to become a leading figure in Soviet astrophysics. Little is known of his personal life, but we know that to be a successful physicist in the Soviet Union required a delicate balancing act. Your research could not be seen to conflict with the official dialectical materialist ideology of the state. You were often pulled away from your own interests to work on state-sponsored, high-priority projects. And the Iron Curtain made it incredibly difficult to communicate your work to the wider international scientific community. And yet, within these constraints, Novikov found enough intellectual freedom to pursue some decidedly unorthodox and brilliant lines of research. And in 1964, he had a great revelation, a revelation that was born from a simple but profound insight into the nature of gravity and time. Imagine you take a video of yourself tossing a ball up into the air and then catching it. If you were to play this video in reverse, it would look perfectly natural. The mathematics that describe the ball's motion under the influence of gravity. The laws of Newtonian mechanics are time-symmetric. They do not have a preferred direction of time. The same is true for the much more complex mathematics of Einstein's general relativity. The equations do not, in themselves, distinguish between the past and the future. They are like a mirror that does not know which is the object and which is the reflection. It is up to us, as physicists, to use our knowledge of the rest of the universe, particularly the second law of thermodynamics, the arrow of time, to decide which of the time-symmetric solutions to the equations are physically plausible. Novikov realized that since a black hole is a particular solution to the equations of general relativity, then its time-reversed counterpart must also be a valid mathematical solution. Instead of an object that traps things forever, a black hole, there could be an object that ejects things forever, a white hole. Novikov, and independently, the Israeli physicist Yuval Ne'eman, proposed this idea as a potential explanation for the mysterious, incredibly bright, and distant objects that were then being discovered by astronomers, objects that we now know as quasars. Perhaps these were not distant galaxies, but white holes in our own galaxy, spewing out matter and energy that had been created in the Big Bang. Because of the political and scientific isolation of the Soviet Union, Novikov's work was largely unknown in the West for many years, but the idea was a stunning one. A white hole would be a truly bizarre and paradoxical object, perhaps even stranger than its black hole twin. It would still have a singularity at its center, a point of infinite density. But this singularity would be in the past, not the future. The white hole would be surrounded not by an event horizon, but by an anti-horizon. It would still have mass, and so you would still be gravitationally attracted to it. But you could never enter it. The anti-horizon is the ultimate exclusive club. It forbids passage into the white hole, just as a black hole's event horizon forbids passage out of it. If you were to find yourself inside a white hole at the moment of its formation, however, you would not stay there for long. You would be propelled outwards, carried on a torrent of space-time that was itself expanding faster than the speed of light, an irresistible river from which you could not deviate until you were ejected from the white hole's anti-horizon. The white hole would continue this process, spewing out all the matter and radiation that had been trapped within it at its creation, until it was completely empty, leaving behind nothing but a bare singularity and its anti-horizon. A white hole is a cosmic ghost, an echo from the past, an explosion that is happening now, but which was set in motion at the beginning of time. In time, astronomers would find a much more natural and compelling explanation for the immense energy of quasars. They are the supermassive black holes at the centers of young, active galaxies. And the intense light they emit is the death scream of the matter that is spiraling into them. The idea of white holes as real, astrophysical objects faded from the mainstream. But as late as 2014, Novikov himself still held out hope that some of the strange, transient events we see in the sky could be the dying embers of primordial white holes, forged in the exotic, unknown physics of the early universe, and still shining today. And while most physicists today have relegated white holes to the dustbin of interesting, but physically impossible, mathematical curiosities, the idea did not die completely. A few brilliant and open-minded physicists were intrigued. One of them was the British mathematical physicist Roger Penrose, who would later go on to win a Nobel Prize for his groundbreaking work on the inevitability of singularities in black holes. Penrose became aware of Novikov's work and realized that it might just be the missing ingredient needed to make sense of another, even stranger, solution to Einstein's equations, a solution that seemed to describe a tunnel, a bridge, from one universe to another. But it would be Penrose's friend and frequent collaborator, the flamboyant and brilliantly imaginative American physicist John Archibald Wheeler, who would take this idea and run with it, who would give these strange cosmic tunnels their modern, evocative name, wormholes. Wheeler realized that the two strange beasts of relativity, the black hole and the white hole, could be stitched together, that they could be two mouths of a single, continuous tunnel through the fabric of space-time. And he realized that the mathematical description of this strange, connected object had, in fact, already been found, decades earlier, by a quiet and relatively unknown assistant of Einstein's. And with that solution in hand, Wheeler saw the dazzling possibility that this obscure mathematical branch of relativity could blossom into something truly extraordinary, a way to travel between the stars, to jump light years in an instant. He just needed to figure out if the machine of general relativity was spitting out a work of profound predictive genius, or a piece of beautiful, but ultimately misleading, mathematical madness. The history of science is filled with stories of unsung heroes, of brilliant minds who made crucial contributions but who, for reasons of personality, of politics, or of simple historical accident, have been largely forgotten, their names relegated to the footnotes of textbooks, forever living in the shadow of the giants of their time. The story of modern physics is, in many ways, the story of Albert Einstein. But Einstein did not work in a vacuum. He was surrounded by a constellation of brilliant collaborators, of friends, of rivals, of assistants, who helped him to develop, to refine, and sometimes to correct his revolutionary ideas. His close friend, Michel Besso, was, in Einstein's own words, the best sounding board in Europe. His first wife, Mileva Maric, was a brilliant physicist in her own right, and the extent of her contribution to his early, groundbreaking work is still a subject of historical debate. And then there was Nathan Rosen. Rosen would meet Einstein for the first time in 1934 at the newly founded Institute for Advanced Study in Princeton. He was a young, smart, and hard-working physicist who had already made a significant, if unheralded, contribution to our understanding of the atomic nucleus. But despite his own considerable intellect, it is unlikely that his name would be remembered today were it not for his 3-year collaboration with the great master of relativity. Rosen had been at Princeton for several months before he finally worked up the courage to knock on the door of the legendary physicist. Einstein was in the middle of a deep conversation with another collaborator, but he immediately put the young, timid Rosen at ease. Rosen later recalled, "I told him about my work, and he seemed interested and asked many questions. After a while, he began telling me about the work he was doing, and before I realized it, the three of us were engaged in a lively discussion." And what followed was a close and fruitful partnership. Officially, Rosen was Einstein's assistant, but their relationship was more like that of a mentor and a gifted student, and eventually a friendship. Rosen was one of the few physicists who was genuinely interested in Einstein's then unfashionable and ultimately doomed quest to unify gravity with electromagnetism, a shared, quixotic passion that likely helped to cement their bond. And it was during this time together, while wrestling with the deep and thorny problems at the heart of Einstein's theories, that Rosen would come up with a remarkable, and at the time, completely overlooked, new possibility from the machine of relativity. Einstein in the 1930s was deeply troubled by two features of modern physics. The first was the appearance of singularities in his own theory of general relativity, these points of infinite density and curvature that seemed to signal a breakdown of the theory itself. The second was the growing consensus in the new field of quantum mechanics that elementary particles, like electrons, were true, point-like entities, with no size or spatial extent. Einstein found both of these ideas to be philosophically and aesthetically repugnant. He was a deep believer in the idea of a field theory of matter, the idea that particles were not fundamental, but were instead localized, stable, and smooth concentrations of a continuous field, like a knot in the fabric of space-time. He was searching for a way to modify his theory to eliminate the ugly singularities and to describe particles as these kinds of smooth, field-like structures. And it was the young Nathan Rosen who came up with a brilliantly ingenious and deeply strange way to do it. Rosen and Einstein imagined what would happen if you could follow a path into a black hole across its event horizon, but somehow avoid the crushing singularity at its center. They asked the machine of general relativity what is the simplest geometric construction that would allow for such a path, and the machine gave them an answer. It showed them that it was possible to mathematically stitch the space-time of a black hole to the space-time of its time-reversed twin, the white hole. The result was a smooth, continuous, and singularity-free geometry. A bridge that connected two different regions of space-time. A particle falling into the black hole would not hit a singularity, but would instead travel through this bridge and emerge from the white hole, either in a different part of our own universe, or, even more bizarrely, in an entirely separate, parallel universe. Rosen and Einstein then tried to take this idea a step further. They added electromagnetic fields to their calculations, hoping that these Einstein-Rosen bridges could serve as their long-sought-after model for elementary particles, with the electric charge of a particle being represented by the electromagnetic field lines that were threaded through the bridge. Unfortunately, this attempt to build a unified field theory of matter did not work. The model did not correctly reproduce the known properties of particles, and so the idea of the Einstein-Rosen bridge, a beautiful and ingenious piece of mathematical physics, fell into relative obscurity. A footnote in the history of a failed research program. It would be another 2 decades before the American physicist John Archibald Wheeler would resurrect this forgotten idea of Nathan Rosen's, dust it off, and give it a new and wonderfully evocative name, the wormhole. Wheeler, with his boundless curiosity and his penchant for asking the big, norming questions, immediately saw the profound implications of the Einstein-Rosen bridge. He was the one who realized that these were not just abstract, mathematical constructs. They were, in principle, tunnels through space-time, shortcuts that could connect distant points in the universe. In principle, you could travel to a star hundreds of light-years away with no more effort than taking a leisurely stroll through a short cosmic tunnel. The dream of interstellar travel, of a future where humanity could become a truly galactic species, seemed to be hidden, in plain sight, in the forgotten equations of Einstein and his young assistant. But almost as soon as he had this exhilarating realization, Wheeler, a master of the complexities of general relativity, also saw the fatal flaws. Rosen and Einstein had imagined a purely geometric and static object. They had not asked the crucial dynamic question that the 4-year-old Wheeler had once asked his mother: what happens when you get to the end of things? What happens when you actually try to travel through one of these wormholes? Wheeler, who was one of the few physicists in the West to have become aware of Novikov's work on white holes, realized that the Einstein-Rosen bridge was a tunnel with a black hole at one end and a white hole at the other. And he knew that both of these objects were deeply, and perhaps insurmountably, problematic. The first fatal flaw is that while our universe seems to be full of physically plausible mechanisms for creating black holes, the collapse of massive stars being the most common, it seems to have no way of creating white holes. The laws of thermodynamics, particularly the second law of increasing entropy, seem to forbid it. The collapse of a star into a black hole is a process that dramatically increases the entropy of the system. It is a natural and thermodynamically favored process. But the time-reversed process, the spontaneous emergence of a star from a white hole, would be a massive violation of the second law, a process of incredible, unspontaneous ordering. It is like expecting a scrambled egg to spontaneously unscramble itself back into a pristine, whole egg. The universe simply does not work that way, even if a primordial white hole had somehow been formed in the exotic, Unknown physics of the Big Bang. It would not be stable. Its anti-horizon is a place of infinite instability. Any tiny amount of matter or radiation falling towards it from the outside universe would be blue-shifted to an infinite energy, causing the white hole to collapse into a black hole in an instant. The universe, it seems, has a deep and powerful prejudice against white holes. They are a mathematical possibility that is forbidden by the rest of physics. But even if you could, by some magical future technology, create a stable white hole and use it as the exit of an Einstein-Rosen bridge, Wheeler realized that you should never, ever enter it. The interior of a wormhole is not a serene, peaceful tunnel. It is a region of the most extreme and violent. Gravitational forces imaginable, the same forces that crush matter at the singularity of a black hole, the tidal forces that would stretch an infalling astronaut into a long, thin strand of atoms in a process that physicists playfully call spaghettification, are at play within the throat of a wormhole. Wheeler's calculations showed that the wormhole is dynamically unstable. The very presence of a particle, or even a single photon of light, attempting to travel through it would be enough to trigger a catastrophic collapse. The wormhole would stretch along its length and compress across its middle, like a rubber band that is stretched too far and snaps. And this collapse would happen faster than the speed of light. Nothing, not even light itself, could travel through the throat of the wormhole and emerge safely from the other side before the tunnel destroyed itself. For a brief, fleeting instant, you might glimpse your destination. Light from the other end of the wormhole can fall into the throat. You could, in principle, see the distant stars of the Andromeda galaxy. You could even meet another, equally unfortunate traveler who had entered from the opposite end. You could share a final, brief, and poignant moment. Two explorers from different ends of the universe, meeting in the heart of a dying, impossible bridge. And then, the wormhole would collapse, and you would be trapped, not in a white hole, but in the familiar, and equally deadly, heart of a black hole. Your only possible destination, the singularity. You would die. Wheeler's devastating analysis, published in the early 1960s, seemed to be the final nail in the coffin for the dream of interstellar travel through wormholes. For decades, most physicists accepted that they were, quite literally, dead ends, a beautiful but ultimately forbidden solution to Einstein's equations. But predictably, that was not quite the end of the story. For decades later, a new generation of physicists, armed with new ideas and a new sense of playful, speculative curiosity, would take up the challenge once again. And it would be one of Wheeler's own. Brilliant former students who would find a new, and even stranger, way to prop open the gates to the stars. He just needed a little help from the world of science fiction. The relationship between science and science fiction is a long, intimate, and often fruitful one. Science fiction writers have often been inspired by the cutting-edge ideas of science, taking them and extrapolating them into strange and wonderful new worlds. And in turn, scientists have sometimes been inspired by the bold, imaginative visions of science fiction, using them as a spur to ask new questions and to explore new theoretical possibilities. The story of the traversable wormhole is a beautiful example of this creative, two-way street. In the mid-1980s, the renowned astronomer and science communicator Carl Sagan was writing his first and only science fiction novel, Contact. The story involved humanity receiving a detailed set of instructions from an advanced, extraterrestrial civilization for building a machine that would allow for interstellar travel. Sagan, a stickler for scientific accuracy, wanted his method of travel to be at least plausible, to be grounded in our best current understanding of physics. He initially considered having his protagonist travel through a black hole, but he knew that this would be a one-way trip to a crushing singularity. So, he turned to his old friend and colleague, the theoretical physicist Kip Thorne, one of the world's leading experts on general relativity and black holes. Sagan asked Thorne a simple question: what is the most plausible, scientific way to get my character from here to the star Vega, 26 light-years away, in a reasonably short amount of time? Thorne, aware of the fatal instabilities of the classic Einstein-Rosen bridge, was initially stumped, but the question intrigued him. It was a well-posed physical problem, and he decided to take it seriously. Working with his graduate students, Michael Morris and Ulvi Yurtsever, Thorne went back to the machine of general relativity. But instead of working it in the usual forward direction, starting with matter and calculating the resulting space-time, he decided to work it in reverse. He started with the desired output, a stable, traversable wormhole, a space-time geometry that would connect two distant points and that would not contain any deadly singularities or event horizons. He then asked the equations the crucial question: what kind of matter or energy would you need to input to create and sustain such a structure? The machine, ever dutiful and completely ignorant of what is and is not physically possible in the real universe, gave him an answer. And the answer was as strange as it was profound: to build and maintain a traversable wormhole, you would need a form of matter or energy with a very peculiar and seemingly impossible property: a large negative pressure, a pressure that is, in fact, greater in magnitude than its energy density. This is what physicists now call exotic matter. This is not to be confused with antimatter, which has a positive mass energy and a positive pressure, just like normal matter. This is something else entirely, something that would have to have a negative mass energy. A football that weighs minus 500 grams, a steak that has a negative caloric content, exotic matter, if it existed, would have bizarre anti-gravitational properties. It would not pull and attract, it would push and repel. It would be the ultimate source of cosmic anti-gravity. And Thorne and his students realized that this was exactly what was needed to solve the two fatal problems of the classic wormhole. A shell of this exotic, repulsive matter, placed at the throat of a wormhole, would act like a cosmic scaffolding. Its anti-gravitational push would counteract the wormhole's natural tendency to collapse. It would hold the throat open, making it stable, and it could be used to push the entrance of the wormhole outside of any event horizon, making it safely traversable. You could enter one end, travel through the stable, open throat, and emerge from the other, without being crushed by tidal forces or trapped by a singularity. The key to the stars, it seemed, was this strange, hypothetical, and deeply problematic substance: exotic matter. Thorne's work, which he published in a 1988 paper, was never intended as a serious proposal for building a wormhole. As the paper's playful subtitle, "A Tool for Teaching General Relativity," suggested, it was primarily a pedagogical exercise, a way to use a fun science-fictional problem to explore the deep and often counterintuitive consequences of Einstein's theory. As Thorne himself said, "Almost everything that I've done was something I never planned to do, but the idea took on a life of its own." It sparked a new wave of research into the theoretical possibilities of wormholes, and it forced physicists to confront a deep and important question: is exotic matter, in any form, actually allowed by the laws of nature? The problem with exotic matter is not just that we have never observed it. It is that its existence would seem to violate some of the most fundamental and cherished principles of physics. A substance with negative mass energy would have deeply paradoxical properties. For example, it would seem to violate the conservation of momentum. If you pushed on an object with negative mass, it would accelerate towards you, not away from you. This would allow you to create a reactionless drive, a device that could accelerate itself without expelling any propellant. a clear violation of Newton's third law. It could also lead to runaway solutions, where a positive mass and a negative mass object would chase each other, accelerating to infinite speed without any input of energy, a clear violation of the conservation of energy. For these reasons, most physicists believe that macroscopic, stable quantities of exotic matter are likely forbidden by the laws of nature. But what about exotic energy? We know from Einstein's famous equation, E=mc², that matter and energy are two sides of the same coin. And the quantum world, we have learned, is a strange and wonderful place, a place where our classical intuitions often fail. And it is in the quantum world that we find a small but tantalizing loophole, the Casimir effect. As we have seen, the energy of the quantum vacuum is not zero, but it is possible to create a region of space where the energy density is less than the normal energy density of the surrounding vacuum. The space between the two parallel metal plates in the Casimir experiment is just such a region. Relative to the outside vacuum, this region has a negative energy density. This is a real, measurable, and experimentally confirmed example of a violation of one of the classical energy conditions, a set of rules of thumb that physicists have developed to distinguish between physically plausible and unphysical solutions to Einstein's equations. The Casimir effect violates the weak energy condition, which states that the local energy density, as measured by any observer, must always be non-negative. However, the Casimir effect is a very small and very localized phenomenon, and it is not yet clear if it is possible to collect and concentrate this negative energy in a way that would be sufficient to stabilize a macroscopic wormhole. There are theoretical arguments, known as quantum inequality theorems, which seem to suggest that while you can have localized pockets of negative energy, they must always be balanced by larger regions of positive energy, and that there are fundamental limits on how much negative energy you can have for how long. The question of whether it is possible to create a sufficient amount of stable, macroscopic negative energy to build a wormhole remains one of the most important and most difficult open questions in fundamental physics. Its answer is likely tied to the still unknown theory of quantum gravity. But the possibility, however remote, remains, and it has given us a new and deeply profound way to think about the nature of space. The same quantum vacuum that is the source of the universe's expansion, the same void that is the cradle of all matter, may also contain the secret to transcending the vast cosmic distances that separate us from the stars. A traversable wormhole, if it is possible at all, would be a thing of true wonder. Its entrance would be a shimmering, spherical portal, not unlike the event horizon of a black hole, but it would not be black. It would be a blaze of light, a window into another part of the universe. Looking into it, you would see the distorted, gravitationally lensed image of the stars and galaxies at its other end. You could wave hello to a friend in another galaxy, and you could, in principle, step through and travel there yourself. The journey through the wormhole's throat, held open by the delicate anti-gravitational pressure of negative energy, would be a strange one. Your view of the outside universe would be warped and distorted in bizarre ways by the extreme geometry of the tunnel. But if it were properly engineered, the tidal forces would be gentle, and you would pass through unscathed, arriving at your destination in a time that could be, from the perspective of an outside observer, shorter than the time it would take light to travel the same distance through normal space. It is a tantalizing and beautiful vision, but a functioning wormhole, as we are about to see, is more than just a bridge to faraway galaxies. It is also, and almost unavoidably, a tunnel into the past. On the 28th of June, in the year 2009, at precisely 12 noon Universal Time, the great astrophysicist Stephen Hawking sat alone in a festively decorated room at the University of Cambridge, surrounded by balloons and a tray of champagne. He was waiting for his guests to arrive, But no one came. After several hours, he departed, and only then, after the party was over, did he send out the invitations. The invitation, beautifully printed and elegantly worded, read, "You are cordially invited to a reception for time travelers." It gave the precise date, time, and coordinates of the party. Hawking's charming and clever experiment was designed to provide a simple, empirical test of the possibility of time travel. "I'm hoping copies of the invitation, in one form or another, will survive for many thousands of years," he later said. "Maybe one day, someone living in the future will find the information and use a wormhole time machine to come back to my party, proving that time travel will one day be possible." The fact that no one showed up was, for Hawking, a compelling piece of evidence that travel into the past is likely not possible. And yet, the very theory that he had dedicated his life to studying, Einstein's general theory of relativity, seems to allow for it, and wormholes are the key. If you could build a stable, traversable wormhole, you could, almost by accident, turn it into a time machine. The recipe is surprisingly simple. You create a wormhole with its two mouths, A and B, initially at rest next to each other. Then, you take one of the mouths, say mouth B, and put it on a spaceship and take it on a round trip at a very high speed, close to the speed of light. According to Einstein's special theory of relativity, time for a moving observer slows down relative to a stationary observer. This is the phenomenon of time dilation. So, when mouth B returns from its journey, its internal clock will be lagging behind the clock of the stationary mouth, A. Let's say, for example, that from the perspective of mouth A, 10 years have passed, but for the traveling mouth B, only 1 year has passed. Now you have a tunnel that connects two different points in time. If you enter mouth A in the year 2010, you will travel through the wormhole and emerge from mouth B in the year 2001. You have traveled 9 years into the past. The wormhole is not just a shortcut through space. It has become a shortcut through time. This possibility, which is a direct and unavoidable consequence of combining the geometry of a wormhole with the principles of special relativity, opens up a Pandora's box of logical paradoxes that have troubled physicists and philosophers for decades. The most famous of these is the grandfather paradox. What if you travel back in time and prevent your own grandfather from meeting your grandmother? Then your parent would never have been born, and therefore, you would never have been born. But if you were never born, how could you have traveled back in time to prevent their meeting in the first place? The logic seems to fold back on itself in an inescapable contradiction. This is just one of a host of similar consistency paradoxes. What if you go back in time and destroy the very wormhole machine that you used to travel back in time? The very act of succeeding in your mission erases the possibility of you ever having undertaken it. Faced with these seemingly insurmountable logical hurdles, physicists who have studied wormholes and time travel have been forced to come up with some ingenious and often bizarre ways to resolve them. The Soviet physicist Igor Novikov, the father of the white hole, proposed what is now known as the Novikov self-consistency principle. He suggested that the laws of physics are such that they forbid any action that would create a paradox. Time travel into the past may be possible, but you are not free to do whatever you want. Your actions are constrained in such a way that they must be part of a self-consistent historical loop. If you travel back in time to try and kill your grandfather, you will fail. The gun will jam, you will slip on a banana peel, you will have a sudden change of heart. The universe, in a sense, will conspire to protect its own. Causal consistency. The past is not changeable, it is fixed. And if you have traveled into it, then your actions were already a part of that fixed history. This is a logically consistent solution, but it is one that seems to do away with the very notion of free will. Stephen Hawking, on the other hand, took a different approach. He proposed what he called the chronology protection conjecture. He believed that the laws of physics themselves must have a built-in mechanism that forbids the formation of closed time-like curves, the technical term for paths through space-time that would allow for travel into the past. He did not know what this mechanism was, but he believed that a full theory of quantum gravity would reveal it. Perhaps the very act of trying to turn a wormhole into a time machine would cause a catastrophic buildup of quantum vacuum energy that would destroy the wormhole in an instant. The universe, in his view, has a chronology protection agency that makes the world safe for historians. A third, and even more radical, possibility comes from the many worlds interpretation of quantum mechanics. In this view, when you travel back in time and alter the past, you do not change the history of your own universe. Instead, your action causes the universe to split into a new, parallel timeline. You have not changed your past, you have created a new one. In this new universe, your grandfather is dead and you will never be born. But in your original universe, nothing has changed. You have simply traveled to a different branch of the multiverse. This elegantly solves the paradoxes, but it does so at the cost of accepting the existence of an infinite number of parallel realities. In this scenario, perhaps there is a universe out there where Hawking's party was a roaring success, attended by a throng of curious and well-behaved time travelers. But in our branch of the multiverse, it was a lonely and ultimately unsuccessful affair. The question of whether wormholes and by extension time travel are possible remains one of the most fascinating and unresolved questions in all of fundamental physics. It is a question that lies at the deep and treacherous intersection of general relativity, quantum mechanics, and the very nature of causality and time. And it is a question that has, in recent years, taken another unexpected twist. In 2019, a team of researchers at Harvard and the Institute for Advanced Study, the very same institution where Rosen and Einstein had first conceived of their space-time bridge, found a way to construct a theoretical, traversable wormhole that did not require any exotic, negative energy at all. But there was a catch. This wormhole, which was constructed in a simplified, toy model of space-time, was not a shortcut. In fact, an analysis of its geometry revealed that the path through the wormhole was actually longer than the path through the surrounding normal space. It was not a cosmic highway. It was a cosmic scenic route. This intriguing, if frustrating, result suggests a new and tantalizing possibility that wormholes may very well be allowed by the laws of nature, but they may also be completely and utterly useless for interstellar travel. The current consensus among most physicists is that traversable wormholes, at least the kind that would allow for faster-than-light travel or time travel, are likely forbidden by a deeper and as yet unknown principle of quantum gravity. But they remain an invaluable theoretical laboratory, a playground for the mind where we can test the limits of our current theories, explore the most extreme configurations of space-time imaginable, and probe the deep and beautiful mysteries that lie at the heart of our understanding of the universe. As Stephen Hawking himself once said, reflecting on the deep and beautiful mysteries of quantum gravity, not only does God play dice, but he sometimes throws them where they cannot be seen. Wormholes may be one of those dice, a hint of a deeper, stranger, and more wonderful reality. A reality that is, for now, hidden from our view. Reality is not as solid as it seems. Beneath the surface of what we call existence lies an intricate and beautiful web of rules. A set of principles so strange and counterintuitive that they defy the very logic we rely on in our everyday lives. Imagine a world where information is not just something we store on hard drives or write in books, but is a fundamental, physical, and a primary building block of reality itself. A world where the basic units of data are not fixed, definite ones and zeros, but are fluid, shimmering, and probabilistic entities, existing in a ghostly superposition of multiple states at once. This is a realm where the very act of observation, of looking at something, changes the nature of what is there. It is a world where two particles, separated by the vast, cold emptiness of galaxies, can be so deeply and mysteriously connected that the actions of one instantly, and without any apparent communication, affect the other. It is a world where a simple measurement can erase a universe of possibilities, collapsing the limitless into the defined, the potential into the actual. This is not the realm of science fiction, of fantasy, or of mystical speculation. This is the world as it is described by our best and most fundamental theory of nature, the theory of quantum mechanics. It is the foundation of the universe itself. For centuries, the clockwork, predictable order of classical physics painted a picture of a reality that was, at its core, understandable and intuitive. But as we have learned to probe deeper into the heart of matter, as our experiments have become more sensitive and our theories more sophisticated, we have found that the smallest scales of nature do not behave as our classical instincts tell us they should. They operate on a different logic, a different set of principles, a set of principles so bizarre that even Albert Einstein, one of the great architects of modern physics, struggled to accept them, famously dismissing one of its key features as spooky action at a distance. What if information is not just an abstract concept that we use to describe the world, but is the very scaffolding upon which reality is built? What if the universe is, in some deep and fundamental sense, a cosmic algorithm, a vast quantum computation that is constantly processing the fabric of existence itself? This is a radical and profound idea, one that is emerging from the confluence of physics, computer science, and information theory. It suggests that the its of the physical world, the particles, the fields, the forces, are all, at their core, manifestations of bits of quantum information. Yet, for all its strangeness and its deep philosophical mystery, the world of quantum information is not just a theoretical curiosity. It is a field that holds the potential to revolutionize our technology, to create new forms of computation, of communication, and of security that were previously unimaginable. It promises to give us unbreakable encryption, to build computers that can solve problems that are intractable for even the most powerful classical supercomputers, to create sensors of unprecedented precision. But could the strange and beautiful rules of quantum information also hold the answers to questions that are even more profound? Could the ultimate nature of reality itself be, at its core, an elaborate and beautiful interplay of quantum codes? Could consciousness, could life, could the very structure of space-time be emergent properties of an underlying informational reality? These are the questions that are driving the next great revolution in our understanding of the cosmos. The deeper we look, the stranger it becomes. The quantum world is a realm where our conventional, classical intuition crumbles into dust. And with it, our understanding of something as seemingly straightforward as information undergoes a profound and radical transformation. In classical physics, information is an abstract and secondary concept. It is something that we use to describe a physical system. It is the bits stored on a hard drive, the words written on a page, the positions and velocities of a set of particles. The information describes the reality, but it is not the reality itself. But in the quantum domain, this clear distinction between the physical system and the information it contains begins to dissolve. Quantum information takes on a physical and even primary identity. This physicality changes the very way we define and process information, endowing it with a strange and powerful set of new properties. Imagine a simple, classical bit of information, like the outcome of a coin flip. It is binary. It can be either heads or tails, a 1 or a 0. But a quantum bit, or qubit, the fundamental unit of quantum information, is not so constrained. Thanks to the principle of superposition, a qubit can be a 0, a 1, or, most remarkably, a ghostly, probabilistic blend of both at the same time. It is like a coin that is not heads or tails, but is spinning forever in a shimmering blur of both possibilities, until the moment it is measured. This non-binary nature of the qubit, its ability to exist in a continuous spectrum of states, adds an incredible complexity and power to the very notion of information. It means that a quantum system can store and process a vastly greater amount of information than its classical counterpart. This is not just a quantitative difference, it is a qualitative one. Quantum mechanics challenges the very deterministic perspective that underpins classical physics. A classical system, like a set of billiard balls on a table, is predictable. If you know the initial positions and velocities of all the balls, you can, in principle, calculate their entire future trajectory with perfect accuracy. But a quantum system is fundamentally, irreducibly probabilistic. You can never know its future with certainty. You can only know the probabilities of the different possible outcomes. This means that a quantum system is not just a matter of having enough data. It demands a complete reevaluation of how we interact with the universe, of the very nature of knowledge itself. Information, in this quantum picture, is not just a passive record of a pre-existing reality. It is an active, dynamic, and participatory entity, something that is woven into the very fabric of physical law. The theory of quantum mechanics suggests that all physical systems are, at their core, carriers of information. But this is not just descriptive, classical information. Quantum information has a set of strange and unique properties that set it apart. Properties that enable transformations and processes that are simply impossible in the classical world. Take, for a moment, the concept of measurement. What actually happens when we look at a quantum system? This question strikes at the very heart of the measurement problem, one of the most contentious and deeply debated puzzles in all of quantum mechanics. As we have seen before it is observed, a quantum particle exists in a superposition of all its possible states. It is like an unread book, a book that contains every possible story, every possible narrative, all at the same time. The moment we read the book, the moment we make a measurement, we seem to force it to choose a single, definite story. The superposition collapses, and one of the many possibilities becomes the single, actual reality. But does this act of measurement represent the creation of information, or are we merely revealing a piece of a pre-existing, but hidden, reality? The paradox deepens when we consider the nature of quantum states themselves. In the classical world, you can measure a property of a system, like the temperature of a cup of coffee, without fundamentally changing the system itself. But in the quantum world, this is not always the case. There are certain quantum states that cannot be fully known without destroying them. The very act of gaining information about the system can irrevocably alter it. Observation is not a passive act. It has a real physical cost. This forces us to rethink the very concept of truth or fact. Imagine two scientists trying to understand the state of a single electron. One scientist decides to measure its position with great precision. The other decides to measure its momentum. According to the uncertainty principle, they cannot both get a precise answer. The first scientist's measurement of the position makes the electron's momentum fundamentally uncertain. The second scientist's measurement of the momentum makes its position fundamentally uncertain. They are not just getting different, incomplete pieces of a single, objective picture. They are, in a sense, creating two different and mutually exclusive realities through their choice of measurement. The complementary nature of quantum systems, the fact that certain properties exist in a trade-off, ensures that our knowledge of the quantum world is always and fundamentally partial. It is not a limitation of our instruments. It is a built-in feature of reality. From this inherent uncertainty, we move to an even stranger and more profound quantum feature entanglement. When two or more particles become entangled, their individual quantum states are no longer independent. They merge into a single, shared state, a single wave function that describes the entire system, regardless of the distance separating the particles. Einstein, as we know, dismissed this as an eerie coincidence, a spooky action at a distance. But today, we know that entanglement is a real physical phenomenon. It binds particles together like invisible, non-local threads stretching across the vastness of the cosmos. Through this strange connection, one particle seems to know the state of its partner instantly, no matter how far apart they are. The measurement of one immediately influences the state of the other. The implications of this quantum entanglement for the nature of information are profound and revolutionary. It opens the door to technologies that were once the sole domain of science fiction: quantum teleportation, for example, is no longer a fantasy. It is a real, experimentally verified phenomenon. When two particles are entangled, it is possible to teleport the quantum state of a third particle onto one of the entangled pair, a process that effectively transfers the information across space without physically moving any matter. While this process does not allow for faster-than-light travel, the classical information needed to complete the teleportation process must still be sent at or below the speed of light. It is a phenomenon that fundamentally redefines our understanding of how information can be communicated. But the quantum world does not just offer new possibilities for information, it also imposes strict and beautiful new limits. The no-cloning theorem, a fundamental principle of quantum mechanics, states that it is impossible to create an identical, independent copy of an arbitrary, unknown quantum state. You cannot simply photocopy a qubit in the same way you can photocopy a classical bit. This is a profound and important feature of the quantum world. It ensures that quantum information has a kind of privacy and integrity that classical information lacks. It is the physical basis for the security of quantum cryptography. It also tells us something deep about the nature of reality. The universe, it seems, does not allow for perfect replication. Each quantum system is, in a sense, unique and unreproducible. The entangled pairs themselves carry their own unique measure of informational complexity, a quantity known as entanglement entropy. This entropy is a measure of the shared, non-local information between the particles, the degree of their interconnectedness. And it is this entanglement entropy that explains why, despite the seeming magic of teleportation, entanglement cannot be used to send free, unlimited, and faster-than-light classical information. There are deep and beautifully consistent rules that govern the flow of information in the quantum world. Underpinning all of these strange and wonderful principles is the ever-present hum of the uncertainty principle. Heisenberg's revolutionary assertion that not all properties of a particle can be known with perfect precision at the same time. This is not just a limit on our knowledge, it is a fundamental feature of the information content of the universe itself. It places a cap on how much useful, classical information can be extracted from any quantum system at a given time. To encode and retrieve data in the quantum world requires a series of deliberate trade-offs, a kind of delicate balancing act that is dictated by the fundamental, complementary nature of reality. The complementarity principle, the idea that certain properties, like a particle's wave-like and particle-like nature, are mutually exclusive but equally necessary for a complete description, is the ultimate expression of this trade-off. You can ask a wave question, or you can ask a particle question, but you can never ask both at the same time. The information you gain about one aspect of reality necessarily costs you clarity in another. This is a profound departure from the classical worldview, where perfect, complete knowledge seems, at least in principle, to be attainable. In the quantum world, knowledge is inherently and beautifully incomplete. All of this complexity, all of this strangeness raises a deep and compelling question about the ultimate nature of reality. Is the universe at its core an informational entity? What if the physical world is not the fundamental reality, but is an emergent phenomenon, a manifestation of a deeper underlying quantum computation? This is not just an abstract philosophical speculation. It is an idea that is gaining traction in the world of theoretical physics. The process of decoherence, for example, can be seen as a kind of bridge between the quantum and classical worlds of information. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional, and entangled nature. The quantum information, the qubitness of the system, is not destroyed, but is rapidly spread out and dissipated into the vast number of degrees of freedom of the environment, becoming, for all practical purposes, irretrievable. This process is what explains why we do not see macroscopic objects like cats in a state of superposition. It is what allows the definite, classical world of our experience to emerge from the fuzzy, probabilistic world of the quantum. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. The idea of quantum information as being primary suggests that our universe might not just obey physical laws. It might embody them as a form of computation. The evolution of the universe, from the Big Bang to the present day, could be seen as a single, vast, and ongoing quantum computation. A process that is constantly processing information and creating new, more complex structures. In this view, particles are not just things, they are carriers of quantum information, data packets that are navigating a vast, cosmic computational architecture. This is a vision that transcends the classical idea of a universe composed of inert matter and forces. It imagines a universe that is, in a very real sense, alive with information. A universe that is constantly thinking, constantly computing its own reality into existence. And this vision has real, practical applications, particularly in the field of cryptography. The very properties of quantum information that make it so strange: superposition, entanglement. The no-cloning theorem are the same properties that make it the basis for a new and revolutionary kind of security: quantum cryptography, and specifically quantum key distribution, is a technology that uses the principles of quantum mechanics to create a provably secure communication channel. By encoding a secret key in the quantum states of single photons and sending them over an optical fiber, two parties can establish a shared, random key that can be used to encrypt and decrypt their messages. The security of this system is guaranteed by the laws of physics. Any attempt by an eavesdropper to measure the photons will inevitably disturb their quantum state, a disturbance that can be immediately detected by the legitimate users. The randomness inherent in quantum measurement also provides a source of true, unpredictable randomness, which is a crucial ingredient for strong encryption protocols. As we look to the future, the development of a quantum internet, a global network that can transmit and process quantum information, could revolutionize not just our security, but our entire information infrastructure. It would be a network that is not just faster or more efficient, but is fundamentally different. A network that is built on the strange and beautiful logic of the quantum world itself. The journey into the heart of quantum information is a journey that is reshaping our deepest understanding of reality. It is a journey that ties together the abstract concepts of measurement, uncertainty, and entanglement, and reimagines them as the constituent parts of a single, unified, informational framework. And it is a framework that does not just describe reality, it actively determines it. From the security of our most sensitive communications to the most profound and existential questions about the nature of the cosmos. Quantum information is shifting our perspective in deep and powerful ways. Could this be the true foundation of reality? Or is it merely a window into an even deeper, more mysterious layer of existence that is still awaiting our discovery? The tantalizing potential of this new science ensures one thing: this quantum narrative is far, far from over. From the relentless march of entropy and thermodynamics to the deepest and most profound mysteries of quantum mechanics, the concept of information serves as a crucial unifying thread, weaving its way through the vast and varied phenomena that define our physical world. To truly understand how profound and fundamental this concept is, we must first consider the intimate and beautiful relationship between information and entropy. A relationship that is at the very heart of the second law of thermodynamics. We see the effects of this law everywhere. The gradual crumbling of a mountain, the slow fading of a cherished memory, the inevitable cooling of a cup of coffee. Entropy is the universe's great, inexorable tendency towards disorder, towards a state of greater probability and lesser structure. It is the physical basis for the arrow of time. But here is where the story takes a fascinating turn. Information, in its purest, most fundamental sense, is a measure of order, of structure, of reduced uncertainty. When a physical system is in a highly ordered, low-entropy state, like a perfectly arranged deck of cards, we have a great deal of information about it. As the system evolves towards a state of higher entropy, as the cards are shuffled, this information is not destroyed, but is dispersed, becoming harder to access. The act of gaining information about a system, of making a measurement, is an act that can, at least locally, reduce its entropy, an act that brings order out of chaos. This beautiful and intricate dance between the disorder of entropy and the order of information was first given a rigorous mathematical form by the American engineer and mathematician Claude Shannon in his groundbreaking work on information theory in the 1940s. Shannon's work, which was originally designed to understand the limits of communication over noisy channels, provided a precise, mathematical definition of information in terms of the reduction of uncertainty, and showed that it was deeply and formally connected to the concept of entropy in thermodynamics. This connection was deepened and made more physical by the work of the physicist Rolf Landauer in the 1960s. Landauer's principle, a cornerstone of the physics of information, established a fundamental link between the abstract, logical operation of computation and the concrete, physical world of energy and heat. Landauer showed that the erasure of a single bit of information from a computational system is not a purely logical act. It has a real physical cost. It must, by necessity, be accompanied by the generation of a small, but unavoidable, amount of heat, an increase in the entropy of the environment. This principle established, once and for all, that computation is not an abstract, disembodied process. It is a physical process, bound by the very same thermodynamic laws that govern the behavior of steam engines and chemical reactions. The metaphysical concept of information was thereby firmly and irrevocably tied to the tangible, material reality of the universe. This intimate relationship between information, entropy, and energy is beautifully illustrated in one of the most famous and enduring thought experiments in the history of physics. Maxwell's demon. In the 19th century, the physicist James Clerk Maxwell imagined a tiny, intelligent being, a demon, who could control a tiny, frictionless door in a partition that divides a box of gas into two chambers. By observing the individual gas molecules, the demon could open the door to let the fast-moving, hot molecules pass into one chamber, and the slow-moving, cold molecules pass into the other. Over time, the demon could create a temperature difference between the two chambers, seemingly decreasing the entropy of the system in violation of the second law of thermodynamics. This paradox puzzled physicists for over a century. The solution, which was finally clarified in the 20th century with the development of information theory, lies in the information processing that the demon must perform. To do its job, the demon must first measure the velocity of each molecule, a process that requires the acquisition of information. It must then store this information in its memory. And finally, it must erase its memory to make room for the next measurement. And it is this act of erasing information that, according to Landauer's principle, must generate entropy, an amount of entropy that is at least as great as the entropy that was seemingly reduced by sorting the molecules. The second law is saved, but at a price. The thought experiment demonstrates, in a beautiful and profound way, how inseparable information is from the physical processes it describes. Information is not a ghostly, non-physical entity. It has a real physical substrate, and its manipulation has real physical consequences. This principle extends to the largest scales of the cosmos. The flow of information in our universe is fundamentally constrained by the laws of relativity. The speed of light is not just the maximum speed at which matter and energy can travel. It is the maximum speed at which information can be transmitted. This cosmic speed limit is what safeguards the principle of causality, the fundamental idea that a cause must always precede its effect. It ensures that the temporal order of events is preserved, that the past cannot be changed by the future. The very structure of space-time, with its fixed and universal speed of light, is a structure that is designed to regulate the flow of information, and it is at the intersection of relativity and information that we find one of the deepest and most challenging puzzles of modern physics. The black hole information paradox. When matter, with all its rich and complex information, falls into a black hole, it seems to be lost to the universe forever, trapped behind the one-way membrane of the event horizon. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be purely thermal, random, and devoid of any of the information that originally fell in. This would represent a fundamental violation of the quantum mechanical principle that information can never be truly destroyed. The resolution of this paradox is thought to lie in the subtle, quantum correlations and entanglements within the outgoing Hawking radiation, a solution that would require a deep and beautiful synthesis of quantum mechanics, general relativity, and information theory. Beyond the realms of classical physics, thermodynamics, and relativity, the role of information becomes even more central when we consider the dynamic, creative, and evolutionary processes of the universe. Despite the second law's relentless push towards greater disorder, the universe is not a uniform, featureless soup of entropy. On the contrary, it is filled with islands of astonishing and beautiful complexity, the intricate structures of galaxies, the fiery hearts of stars, the delicate and purposeful machinery of living organisms. These ordered structures are not a violation of the second law. They are a consequence of it. They are what the Nobel laureate Ilya Prigogine called dissipative structures. Open systems that maintain their internal order by importing energy from their environment and exporting entropy. A star, for example, is a highly ordered system that maintains its structure by consuming the low-entropy fuel of hydrogen in its core and radiating high-entropy heat and light into the surrounding space. Life is the ultimate example of this process. A living organism is an island of incredible, localized order, a system that actively works to maintain its structure and to create new knowledge, all while increasing the overall entropy of the universe around it. The process by which these complex, ordered structures emerge is known as self-organization, and information is the silent guiding architect of this process. The flow of energy through a system is not enough to create complexity. There must also be an informational blueprint, a set of rules or constraints that guides the self-organizing process. In the formation of a snowflake, this blueprint is provided by the crystalline structure of water and the laws of thermodynamics. In the formation of a galaxy, it is provided by the laws of gravity and the initial density fluctuations in the early universe. And in a living organism, it is provided by the rich and unimaginably complex information encoded in the DNA molecule. This can be understood through the statistical interpretation of entropy, first developed by Ludwig Boltzmann. Boltzmann showed that the entropy of a system is related to the number of possible microscopic arrangements of its constituent parts that correspond to the same macroscopic state. A disordered, high-entropy state, like a shuffled deck of cards, is a state that can be realized in a vast number of different ways. An ordered, low-entropy state, like a deck of cards arranged in perfect numerical and suit order, is a state that can be realized in only one way: information. In this picture is what allows a system to find its way to these rare, improbable, and highly ordered states. The information in the DNA molecule, for example, guides the complex process of protein synthesis, ensuring that the right amino acids are assembled in the right order to create the functional machinery of the cell. It is a process that carves out a tiny, highly ordered path through a vast, chaotic landscape of possibility. The arrow of time, then, is a story of two competing tendencies. On the one hand, there is the relentless universal drive towards greater entropy, towards disorder and heat death. But on the other hand, there is the creative, local, and information-driven process of self-organization, a process that builds islands of exquisite and beautiful complexity against this cosmic tide. Life is the most remarkable and poignant expression of this creative countercurrent. It is a process that thrives by absorbing energy and processing information, a process that creates pockets of meaning and purpose in a universe that is, on the whole, becoming more meaningless and purposeless. And at the heart of this creative process lies the mysterious and powerful role of information. The principles of information are not just at play in the grand cosmic drama of stellar and biological evolution. They are also at the heart of the strange and beautiful world of quantum mechanics, at the smallest scales of reality. The very act of gaining information about a system, the act of measurement, is a process that fundamentally changes the state of that system. This is the basis of the thermodynamics of measurement, a field that explores the deep and intimate connection between information, entropy, and the quantum world. When we measure a property of a quantum particle, like its spin or its position, we are extracting information from it. But this is not a passive act. The measurement process itself is an irreversible, entropy-increasing interaction. It is the process by which the ghostly, probabilistic world of quantum superposition is collapsed into the definite, singular reality of our classical experience. The process of decoherence is the mechanism by which this happens. A quantum system is never truly isolated. It is always interacting, however subtly, with its environment, the information about its delicate superpositional state leaks out into the vast number of degrees of freedom of the surrounding world, becoming, for all practical purposes, irretrievably lost. This is what gives the quantum world its classical appearance. The definite, stable reality we perceive is a consequence of the constant entropic loss of quantum information into the environment. Perhaps one of the most exciting and forward-looking applications of these ideas is in the field of quantum computation. A classical computer processes information one logical step at a time, but a quantum computer, by harnessing the principle of superposition, can explore a vast number of computational paths simultaneously. This quantum parallelism gives it the potential to solve certain problems, like factoring large numbers or simulating complex quantum systems at a speed that is exponentially faster than any classical machine. This is a technology that could revolutionize science, medicine, and artificial intelligence. And as we look to the future, the frontier of information physics hints at even more radical and profound insights. Some researchers, in their quest for a theory of quantum gravity, have proposed that the very fabric of space-time may be, at its core, an informational construct. The holographic principle, for example, theorizes that all the information contained within a three-dimensional volume of space can be completely described by the information encoded on its two-dimensional boundary, like a hologram. If this is true, it would mean that information is not just a property of reality. It may be the very substance of reality itself. Furthermore, a deeper understanding of the thermodynamics of information could lead to a new generation of hyper-efficient technologies. By leveraging principles like Landauer's limit, we might one day be able to build computational and communication systems that operate at the absolute physical limits of energy efficiency. A future where our technological progress is guided not by the raw consumption of energy, but by the subtle and intelligent manipulation of information. And so, as our journey through the world of information comes to a close, we are left with a profound and tantalizing question. What if the universe itself is, at its most fundamental level, a vast, interconnected, and self-organizing field of information? If so, then every star, every planet, every living being would be a constituent part of a grand cosmic informational matrix, a matrix that is constantly evolving, constantly learning, constantly creating new forms of order and complexity. Understanding this deeper, informational reality might not just unlock the next technological revolution. It might also reveal our true place in the intricate and beautiful dance of order, chaos, and knowledge. Information, once seen as a mere abstract description of the world, now emerges as the very scaffolding upon which the universe is built. From the inexorable increase of entropy to the creative process of self-organization, from the strange logic of the quantum world to the grand evolution of the cosmos. It is the thread that illuminates our path towards a deeper and more unified understanding of what energy and matter alone could not explain. As we continue to probe the mysteries of information and its physical manifestations, one thing becomes clear: the story of the universe is not just about what it is made of, but about what it communicates. And in learning to read this cosmic message, we are not just deciphering the secrets of the universe. We are, in a very real sense, discovering our own. Life, at its very essence, can be understood as a profoundly sophisticated and ancient information processing system. Every single cell in your body, from the neurons in your brain to the muscle fibers in your heart, operates like a tiny, powerful, and exquisitely designed biological computer, constantly handling a vast and complex flow of information to sustain the miracle of your existence. And the source code for this incredible biological software is not written in silicon, but in the elegant double helix structure of the DNA molecule. DNA is not just a chemical. It is nature's own time-tested programming language, a biological script that has been written, edited, and refined over the course of nearly 4 billion years of evolution. This single, remarkable molecule, present in almost every cell of your body, contains the complete set of instructions, the architectural blueprint, that guides everything from the division of your cells to the synthesis of the proteins that are the workhorses of your biological machinery. It is a vast and ancient library of life, a library where every book is a gene, and every chapter contains a piece of the accumulated evolutionary wisdom of your ancestors. The process of evolution itself can be seen as the ongoing editing and refinement of this great genetic library. Through the random, mutational process of trial and error, life is constantly experimenting with new editions of its own chapters. Random changes in the genetic information, mutations, recombinations, and the more subtle epigenetic modifications that can be influenced by the environment create a constant stream of new variations. Natural selection then acts as a harsh, but ultimately creative, editor. Those variations that happen to provide a survival or reproductive advantage in a particular environment are preserved and passed on to the next generation, while those that do not are discarded. This process, repeated over countless generations, is not just a random walk through the space of possibility. It is a powerful optimization algorithm, a process that allows life to learn, to adapt, and to accumulate an ever-growing repository of knowledge about how to thrive in an often hostile and unpredictable universe. These principles of biological information processing are not just metaphorical. They are deeply and formally connected to the mathematical principles of information theory, a field that was originally developed to understand the transmission of data in man-made communication systems. The rules of information fidelity, of redundancy, of error correction, are just as relevant to the replication of a DNA molecule as they are to the transmission of a digital file over the internet. The genetic code, for example, is brimming with built-in safety mechanisms. It has a degree of redundancy, where multiple different codons can code for the same amino acid, providing a buffer against some mutations. And our cells have evolved a sophisticated and complex machinery of DNA repair enzymes, molecular proofreaders that constantly scan the genome for errors and correct them, ensuring that the vital instructional information is preserved with an incredible degree of fidelity. But this stability does not stifle evolution. On the contrary, it provides the stable, reliable foundation upon which the creative process of variation and selection can occur. The story of life's information processing continues in the intricate, dynamic, and beautiful networks of communication that exist within and between our cells. The flow of information from the genetic archive of the DNA to the functional machinery of the cell is a marvel of molecular engineering. In a process called transcription, a segment of the DNA is copied into a messenger RNA molecule. This mRNA molecule then travels out of the nucleus and into the cytoplasm, where, in a process called translation, its sequence is read by a molecular machine called a ribosome, which assembles a specific protein, amino acid by amino acid, according to the genetic instructions. This is the central dogma of molecular biology, the fundamental flow of information from DNA to RNA to protein. And it is a process that is happening trillions of times a second in your body right now. The way our cells process this vast amount of data is a masterclass in decentralized, distributed computing. There is no central processing unit, no single brain of the cell. Instead, the cell is a complex, self-organizing network of interacting molecules, a symphony of biochemical signals where each part is in constant communication with the whole. allowing the cell to respond and adapt to its constantly changing environment in a remarkably efficient and robust way. The role of information in building the complexity of life becomes even more apparent when we consider the great evolutionary transition from single-celled organisms to multicellular life. This was a leap that required a complete and radical restructuring of how biological information is stored, processed, and transmitted. Multicellular organisms had to invent new ways to coordinate the functions of billions and even trillions of interconnected cells to ensure that they all work together for the good of the whole. The emergence of the nervous system was a key innovation in this process. The neural network of an animal is an advanced biological supercomputer, a system that is dedicated to processing the vast amount of sensory information from the environment, to driving complex behaviors, and to fostering the process of decision-making. But life's ingenuity in information processing is not limited to the top-down control of neural systems. At the other end of the biological spectrum, we find phenomena like horizontal gene transfer in bacteria, a process where single-celled organisms can directly exchange genetic information with each other, even across species boundaries. It is a kind of biological internet, a peer-to-peer network that allows for the rapid spread of useful genetic innovations, like antibiotic resistance, through the microbial world. These different strategies, the centralized processing of a nervous system and the decentralized network of horizontal gene transfer, are both powerful examples of how life, at every scale, is constantly experimenting with new and more efficient ways to handle the challenges of evolutionary adaptation. Adaptation itself, at its very core, is a process of changing how information is processed and utilized. Organisms are not passive slaves to their genetic programming. They are active, learning systems that are constantly adjusting their internal and external information strategies in response to the pressures of their environment. The process of learning and memory, for example, which is so highly developed in species like birds and mammals, is a powerful adaptive mechanism. It allows an organism to store information about its past experiences, the location of a food source, the presence of a predator, and to use that information to make better, more informed decisions in the future. The environment itself acts as a constant stream of feedback, a set of data that shapes and refines these learning processes, forcing life to operate like a complex, adaptive algorithm that is constantly working to maximize its efficiency and its chances of survival. The influence of information becomes even more profound and fascinating when we consider how these evolutionary processes extend beyond the realm of biology and into the realm of culture and cognition. The evolution of language in human beings, for example, was not just the development of a new way to make sounds. It was a revolutionary leap in the technology of information storage and transmission. Language allowed knowledge to be accumulated, shared, and built upon across generations. A process that is far more rapid and powerful than the slow generational transfer of genetic information. Language is, in a very real sense, a form of externalized biological information. A mimetic code that has allowed human culture to evolve and adapt at a breathtaking pace. And over the course of our history, we have continued to extend the principles of biological information processing into our artificial systems, from the invention of writing and the printing press to the development of the digital, computational marvels that define our modern world. Even the nature of intelligence itself is deeply and inextricably tied to the way that organisms process and utilize information. The increased complexity of the neural connections in the brains of so-called intelligent species is a direct reflection of the growing need to analyze, to store, and to respond to an ever-increasing amount of data from a complex and ever-changing environment. Human cognition, and by extension, human intelligence, has co-evolved with these powerful information processing abilities. To be intelligent is not just to be able to think, it is to be able to efficiently acquire, to analyze, to synthesize, and to translate information into effective, purposeful action. Understanding these deep and beautiful connections between biology, information theory, and evolution paints a new and compelling portrait of life. It is a narrative of constant change, of relentless refinement, and of beautiful adaptation. A narrative in which information lies at the very heart of everything. Life does not evolve randomly. It evolves systematically, constantly finding new and more ingenious ways to process, to store, and to leverage its vast and growing informational wealth in order to thrive against the odds. The evolutionary journey of life, from the first self-replicating molecule to the complex, global civilization of our own species, is not just a story of the survival of the fittest. It is the story of the survival of the most informationally adept. And as we stand at this unique moment in history, as we begin to create new, artificial forms of intelligence, we are not just continuing this evolutionary process. We are, perhaps, on the verge of accelerating it in ways that are both thrilling and deeply, profoundly unsettling. The story of life is the story of information, and it is a story that is far, far from over. The quantum phenomenon of entanglement is not just a strange and counterintuitive curiosity of the subatomic world. It is an experimentally verified reality, a feature of the cosmos that forces us to fundamentally reevaluate our classical notions of space, of distance, and of connection. It is the discovery that two or more particles can share a single, unified quantum state, a relationship so profound and immediate that it seems to challenge the very locality of reality. The idea that objects can only be influenced by their immediate surroundings. But this is where the story gets even stranger. The concept is so bizarre that it deeply troubled even Albert Einstein, who, along with his colleagues Boris Podolsky and Nathan Rosen, famously labeled it spooky action at a distance. In their 1935 paper, they constructed the EPR paradox, a thought experiment designed to show that the predictions of quantum mechanics were so strange that the theory must be incomplete. They argued that if quantum mechanics was right, then particles could seemingly communicate faster than the speed of light, a clear violation of one of the most fundamental principles of his theory of relativity. For Einstein, this spookiness was a sign that there must be some local hidden variables, some unknown properties that the particles carried with them that were predetermining the outcomes of the measurements, thus preserving the comforting classical notion of locality. For decades, this was a philosophical debate, but in the 1960s, the physicist John Bell, in a stroke of brilliant insight, formulated a mathematical theorem, now known as Bell's theorem, which provided a way to experimentally test the predictions of quantum mechanics against any possible local hidden variable theory. Bell's theorem, and the numerous, increasingly precise Bell test experiments that have been performed in the decades since, have delivered a stunning and unambiguous verdict. The inequalities derived by Bell have been overwhelmingly violated, time and time again, confirming the non-local predictions of quantum mechanics and ruling out the possibility of any local hidden variable explanation. The spooky action is real. The universe is, in some deep and fundamental way, non-local. This does not mean that we can use entanglement to send faster-than-light signals and violate causality. But the underlying instantaneous connection is undeniably there. It tells us that our intuitive picture of a universe made up of separate, independent objects is an illusion. The answer to how this happens lies in the strange nature of quantum measurement. When we observe or measure one of the entangled particles, its wave function, the cloud of its possibilities, collapses and it settles into a definite state. And because the two particles are part of a single, unified quantum system, this collapse is not a local event. The entire entangled wave function collapses at once, and this means that the state of the distant, unmeasured partner is also instantly determined. This phenomenon of wave function collapse raises profound questions about the role of the observer in defining reality. Is the universe fundamentally deterministic, with the collapse just revealing a pre-existing state? Or does the act of observation itself play a creative role in shaping the outcome? This brings us to the concept of decoherence, a process that helps to bridge the gap between the strange, superpositional world of the quantum and the definite, classical world of our experience. Decoherence explains how a quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence, its ability to be in a superposition of states. The information about the superposition leaks out into the environment, making it practically impossible to observe. This is why we do not see macroscopic objects in a state of superposition. But decoherence does not fully solve the measurement problem, it just pushes it back. Different interpretations of quantum mechanics, from the traditional Copenhagen interpretation to the radical many worlds interpretation, continue to wrestle with this deep, conceptual riddle. The profound implications of quantum entanglement extend far beyond the realm of theoretical physics and into the world of revolutionary new technologies. The strange, non-local connection between entangled particles is not just a philosophical puzzle. It is a powerful new resource that we are just beginning to learn how to harness. Take, for example, the field of quantum cryptography. The security of our current classical communication systems is based on the computational difficulty of solving certain mathematical problems, like factoring large numbers. But a sufficiently powerful quantum computer could, in principle, solve these problems easily, rendering much of our current encryption obsolete. Quantum cryptography offers a new and fundamentally more secure paradigm. By using entangled photons to create a secret, shared key between two parties, a process known as quantum key distribution, it is possible to create a communication channel whose security is guaranteed not by computational complexity, but by the fundamental laws of physics. Any attempt by an eavesdropper to intercept and measure the photons will inevitably disturb their entangled state, a disturbance that can be immediately detected by the legitimate users. It is a system that is, in principle, unhackable. Similarly, the phenomenon of quantum teleportation, once the stuff of science fiction, is now a routine, if still small-scale, laboratory experiment. It uses the principles of entanglement to transfer the complete quantum state of a particle from one location to another, without physically moving the particle itself. This is not the beaming up of Captain Kirk, but it is a revolutionary new way to think about the transmission of information, a process that could one day be the foundation of a quantum internet, a global network that can transmit and process quantum information. And it is in the field of quantum computing that the power of entanglement is most fully realized. A classical computer processes bits of information that are either a 0 or a 1. A quantum computer uses qubits, which can be in a superposition of both. But the true power of a quantum computer comes from its ability to entangle these qubits. By entangling a large number of qubits, a quantum computer can create a vast, multidimensional computational space, allowing it to explore an astronomical number of possibilities simultaneously. This quantum parallelism is what gives a quantum computer the potential to solve certain problems, from designing new drugs and materials to breaking complex codes at a speed that is exponentially faster than any classical machine. The strange, non-local bond of entanglement is what allows the qubits to work together in a coherent, powerful harmony, unlocking a level of computational power that was previously unimaginable. But what if the significance of entanglement extends even beyond the realms of technology and into the very fabric of space-time itself? Some of the most exciting and speculative ideas in modern theoretical physics suggest that entanglement may not just be a phenomenon that happens in space-time, it may be the very thing that creates space-time. The ER equals EPR conjecture, proposed by the physicists Juan Maldacena and Leonard Susskind, is one of the most provocative of these ideas. It suggests a deep and surprising equivalence between two seemingly disparate concepts, quantum entanglement and wormholes. The conjecture posits that when two particles are quantum mechanically entangled, they are, in a sense, connected by a microscopic wormhole. This is a staggering idea. It suggests that the strange, non-local connection of entanglement is actually a manifestation of a deeper, geometrical connection in a higher dimensional space. It implies that the geometry of spacetime is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is woven from the intricate and complex web of quantum entanglements between the fundamental constituents of the universe. In this view, space is not the thing that separates us. It is the thing that connects us. A vast network of quantum threads, this idea, while still highly theoretical, provides a powerful and beautiful new lens through which to view the universe. It offers a potential path towards a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. It suggests that the deep puzzles of quantum mechanics and the deep puzzles of general relativity may be two sides of the same informational coin, and it has profound philosophical implications. If the fabric of reality is woven from the threads of entanglement, then the universe is not a collection of separate, independent objects, but a single, holistic, and deeply interconnected whole. This is a worldview that resonates with the deepest intuitions of many spiritual and contemplative traditions. The idea that we are all one is not just a poetic sentiment. It may be a deep, physical truth, a truth that is written in the non-local, entangled language of the cosmos itself. The implications of this for our own human experience are vast and largely unexplored. If our own consciousness is, as some have speculated, a quantum phenomenon, then we too may be part of this universal entangled web. The feelings of empathy, of connection, of collective consciousness may not be just psychological phenomena, but may have a real, physical basis in the entangled nature of our own being. Imagine a future where entanglement is not just a topic for the laboratory, but a practical and integrated part of our everyday lives. Our most sensitive data is transmitted with perfect security through quantum encrypted networks. Quantum computers are solving some of humanity's most pressing problems, from climate change to disease, and perhaps even our understanding of ourselves, of our own interconnectedness, will have been transformed by this deep quantum insight, for all its promise. Entanglement reminds us that the universe retains its deep and beautiful mysteries. It challenges our most basic intuitions about causality, about distance, about reality itself. It urges us to rethink our place in a cosmos where the boundaries between here and there, between now and then, between self and other, may be far more fluid and far more mysterious than we ever imagined. What we have uncovered so far is merely the tip of a vast and magnificent iceberg. And with each new experiment, with each new theoretical insight, the strange and beautiful world of quantum entanglement continues to provoke, to puzzle, and to inspire. It is an invitation, not just to scientists, but to all of us, to look closer, to think deeper, and to imagine a universe that is far more interconnected and far more wonderful than it first appears. The universe is a sprawling and often bewildering enigma, a puzzle that has captivated the greatest minds of humanity for centuries. We have observed its patterns, we have dissected its laws, and we have spun beautiful, intricate theories about its origins and its destiny. But what if we were to told you that the very fabric of reality itself could be understood in a radically new and powerful way? What if the universe, in all its vastness and complexity, operates not like a grand clockwork machine, but like a colossal and unimaginably powerful quantum computer? This is a paradigm-shifting idea, one that is emerging from the frontiers of theoretical physics and computer science. It is a vision that reframes our understanding of reality, suggesting that at its most fundamental level, the cosmos may not be made of matter and energy, but of information, and that the laws of physics are not just a set of static rules, but are a form of ongoing, dynamic computation. This concept of a computational universe blurs the line between the observer and the observed, between the physical and the informational, in a way that is both deeply challenging and profoundly beautiful. At the heart of this new paradigm lies a radical reinterpretation of the laws of physics themselves. The equations and the constants that we have so carefully mapped, from the elegant mechanics of Newton to the curved space-time of Einstein and the probabilistic waves of quantum mechanics, may be better understood not as a description of reality, but as the operating system for reality. They are the rules, the algorithms, that govern how the state of the universe is processed and evolved from one moment to the next. Quantum mechanics, in this picture, becomes the fundamental programming language of the cosmos. It is a language that is not deterministic, but probabilistic. It does not deal in absolute certainties, but in a rich and complex landscape of possibilities. The wave function of a quantum system is not just a mathematical tool, it is a complete, informational description of that system, a catalog of all its potential states. And the process of measurement, the infamous collapse of the wave function, is a computational step, a moment when the vast, superpositional potential is processed and a single, definite output is rendered into our classical reality. The ongoing mathematical dance of quantum mechanics is what gives the universe its structure, its texture, and its very existence. Look deeper into this computational cosmos, and you will find the principle of quantum superposition, the astounding ability of a particle to exist in multiple states simultaneously. If you have heard of Schrödinger's cat with its ghostly existence between life and death, you have already grasped the central paradox of this concept. But on a computational level, superposition is not a paradox. It is a resource. It is the basis for a massive and natural form of parallel processing. A classical computer must handle a computation one step at a time in a linear sequence. But a quantum system, by virtue of its ability to exist in a superposition of all possible states, can explore a vast number of computational paths all at once. This opens up a breathtaking possibility. What if the universe itself is performing a kind of continuous, massive parallel computation? What if every quantum event, every collapse of a wave function, is a moment of information processing, creating ripples of newly computed reality that propagate through the cosmos? This would suggest that the universe has an inherent and almost unimaginable computational efficiency, a power that is far beyond anything we could ever hope to achieve with our own man-made technologies. Central to this model of a computational universe is the role of measurement. As we have seen, a quantum system exists as a cloud of possibilities until an observation forces it to collapse into a single, definitive state. In the same way, a computation is not just a sequence of potential solutions. It must, at some point, result in a definite output. The observer in this picture is not just a passive element of reality. They are an active and perhaps even necessary participant. Every time we make a measurement, every time we interact with the world in a way that resolves a quantum uncertainty, we are, in a sense, contributing to the ongoing computation of the universe's state. We are not just reading the cosmic code, we are helping to write it. But what happens when errors arise in this incredible cosmic system? Just as our own computers are prone to glitches and bugs, the universe is not immune to the disruptive influence of quantum noise and decoherence. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional nature. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. This could be seen as a form of error. But what if the universe has a built-in mechanism for quantum error correction? This is a concept that is at the very forefront of the development of real-world quantum computers. The idea of encoding quantum information in a redundant way, so that it can be protected from the effects of decoherence. Could it be that the universe itself employs a form of natural quantum error correction? Could the remarkable stability and consistency of our physical laws be a consequence of an inherent informational redundancy in the fabric of reality? A system that is constantly correcting errors as they arise and preserving the deep computational integrity of existence. The computational nature of the universe is also reflected in the strange, non-local structure of quantum causality. In our classical world, cause and effect follow a clear linear chain of events. But in the quantum realm, as we have seen with entanglement, the relationships between events can be far more subtle and interconnected. Entanglement creates a form of spooky, non-local connection between particles that defies our classical intuition about space and distance. If we translate this into a computational model of the universe, it suggests that the flow of information may not be a simple, linear process. It may follow the intricate, entangled pathways of the quantum world. The processing of reality is not a straight line, but a complex, interconnected web, a graph of relational information where the state of one part can instantly influence the state of another, no matter how far apart they are. This leads to an even more radical idea. What if space-time itself is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is born from the processing of quantum information? Some of the most advanced theories of quantum gravity, like the holographic principle, suggest that the three-dimensional space we experience may be a projection, a hologram that is encoded on a two-dimensional informational surface at the boundary of our universe. In this view, the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space, the flow of time, the force of gravity. All of these could be emergent properties of a deeper, underlying quantum computation. We can see hints of this computational logic even in the processes of the natural world. Quantum algorithms, like Shor's algorithm for factoring numbers or Grover's algorithm for searching a database, are specific, highly efficient solutions that are optimized for quantum systems. And intriguingly, some of these quantum computational strategies share deep structural parallels with natural processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field. It is as if nature itself has, over billions of years of evolution, discovered and implemented some of the most efficient quantum algorithms. This brings us to the most tantalizing and most speculative hypothesis of all. If the universe is indeed a quantum computer, could reality itself be an intricately coded simulation? The simulation hypothesis. The idea that our entire existence might be a program running on a vast cosmic computer is one that has long been a staple of science fiction, but it is now being seriously considered by some physicists and philosophers. If this were true, it would provide a natural explanation for some of the strange, built-in limits of our universe, like the speed of light or the Planck length. These would not be arbitrary constants, but would be the processing speed and the pixel size of the underlying computational reality. The view of the universe as a quantum computational system does not just reframe our understanding of the physical world. It opens up vast, new frontiers for exploration. It forces us to reconsider age-old philosophical questions in the new and powerful light of physics and computer science. If the universe is computing reality, then to understand that computation would be to understand the ultimate nature of existence, and perhaps it would grant us an unprecedented ability to interact with and to shape that reality, to move from being just a variable in the cosmic algorithm to becoming one of its programmers. This perspective does not reduce the awe and wonder of existence. It enhances it. It imagines a cosmos that is alive with a ceaseless and almost unimaginably complex process of calculation, a universe that is mathematically encoding and processing every atom, every star, every galaxy. And it is a reality in which you, the conscious observer, are a crucial and integral participant, not a passive recipient of information, but a node in the network, influencing the system and being influenced by it, connected through the invisible, entangled threads of quantum information to every other part of this incredible, unending equation. Imagine for a moment that this vast, three-dimensional universe, with all its depth, its substance, its seemingly solid reality, is not as it seems. What if everything we experience, the space that separates us, the time that flows around us, the very matter that makes up our bodies, is an elaborate and beautiful projection, a cosmic hologram? What if our entire, rich, three-dimensional world is, in fact, a higher-dimensional mirage? Its information compressed and encoded onto a simpler, two-dimensional canvas at the very edge of our cosmos. This startling and deeply counterintuitive idea is at the heart of what physicists call the holographic principle, and it is a concept that challenges the very fabric of reality as we know it, suggesting a universe that is fundamentally informational, a universe where the distinction between the container and the contained, between the boundary and the bulk, is not as clear as we once thought. The origins of this revolutionary idea lie in one of the most unlikely and most mysterious corners of the cosmos, the study of black holes. For decades, black holes were seen as the ultimate information destroyers. Their immense gravity creates an event horizon, a one-way membrane from which nothing, not even light, can escape. Any information that falls into a black hole seems to be lost to the universe forever, a direct violation of the fundamental quantum mechanical principle that information can never be truly destroyed. In the 1970s, the physicist Jacob Bekenstein, and later Stephen Hawking, discovered something remarkable. They found that the entropy of a black hole, a measure of its information content, is not proportional to its three-dimensional volume, as one would expect, but is proportional to the two-dimensional area of its event horizon. It is as if all the information about the three-dimensional objects that have fallen into the black hole is somehow stored or encoded on its two-dimensional surface. This was the first hint of the holographic principle. It was a suggestion that the information content of a region of space is not as extensive as it seems, that it can be fully described by a theory that lives on its boundary. This idea was given a precise mathematical form in the 1990s by the physicist Juan Maldacena in what is now known as the ADI-CFT correspondence. This is a profound and powerful duality, a kind of mathematical Rosetta Stone that shows a precise equivalence between two, seemingly very different, physical theories. On one side of the duality, we have a theory of gravity, like string theory, that lives in a curved, five-dimensional anti-de Sitter space. On the other side, we have a quantum field theory, a conformal field theory that has no gravity and lives on the flat, four-dimensional boundary of that space. The correspondence states that these two theories are completely equivalent. Every question you can ask in the five-dimensional gravitational theory has a corresponding and equally valid question in the four-dimensional quantum field theory on the boundary. This is a stunning and revolutionary idea. It suggests that gravity itself, which we have long considered to be one of the fundamental forces of nature, may not be fundamental at all. It may be an emergent phenomenon, a holographic projection of a deeper, non-gravitational quantum reality that lives on a lower dimensional surface. The three-dimensional world of our experience, with all its gravitational complexity, could be a hologram generated by the quantum interactions of particles on a distant, two-dimensional screen. This holographic vision of the universe has profound implications for our understanding of space and time. If the geometry of space-time is an emergent holographic property, then it may not be a smooth, continuous fabric at its most fundamental level. It may be quantized, made up of discrete, indivisible units, like the pixels on a computer screen. The search for this holographic noise, the subtle quantum graininess of space-time, is an active, if highly challenging, area of experimental physics. High-energy experiments at particle accelerators and precise, astronomical observations of the cosmic microwave background are both searching for the faint, indirect clues that could reveal the pixelated nature of our reality. If the holographic principle holds true, it would also force us to rethink our most basic notions of causality and locality. In a holographic universe, the idea that events are determined by their local causes and effects may no longer be the fundamental story. The unfolding of events in our three-dimensional bulk would be dictated by the complex, non-local quantum correlations and entanglements of the information on the two-dimensional boundary. The universe would be, in a very real sense, a holistic and interconnected system, where the part is always a reflection of the whole. This perspective also offers a new and powerful way to think about the nature of gravity itself. The physicist Eric Verlinde, building on the holographic principle, has proposed that gravity is not a fundamental force, but is an entropic force. It is an emergent phenomenon that arises from the thermodynamic principles of information. In this view, gravity is a consequence of the universe's tendency to maximize its entropy, a statistical force that pulls things together because it is the most probable configuration of the underlying informational degrees of freedom. This is a beautiful and compelling idea, one that connects the geometry of space-time directly to the laws of information and thermodynamics. And the mathematical architecture for exploring these holographic ideas is provided by the powerful framework of quantum field theory, and particularly conformal field theory. These theories describe how the information on a lower dimensional boundary can give rise to the rich and dynamic phenomena of a higher dimensional space. The study of these intricate mathematical mappings is one of the most exciting and productive areas of modern theoretical physics, and it is providing us with new and powerful insights into the deep, and as yet unsolved, challenge of quantum gravity. The holographic principle offers a compelling and beautiful starting point for unifying the two great, and seemingly incompatible, pillars of modern physics, general relativity and quantum mechanics. It suggests that they may be two different, dual descriptions of the same, underlying informational reality. Beyond its revolutionary implications for physics, the idea of a holographic universe raises a host of deep and unsettling philosophical questions. If our familiar three-dimensional world is, in some sense, an illusion, a projection of a more fundamental, two-dimensional reality, then what does this say about the nature of existence itself? Are we, as conscious three-dimensional beings, just complex patterns in a cosmic hologram? What are the ultimate limits of our knowledge, if the reality we are trying to understand is not the fundamental one? These are questions that push the boundaries of science and steer us into the deep, and often murky, waters of metaphysics, of epistemology, and of existentialism The holographic principle is a profound and humbling reminder of the potential limitations of our own evolved cognition. Our senses, our brain, have been shaped by the pressures of natural selection to be effective tools for surviving and reproducing in a three-dimensional, macroscopic world. They are not necessarily designed to perceive the ultimate, fundamental nature of reality. The world we experience is a user interface, a simplified, and likely very partial, representation of a much deeper and far stranger underlying reality. But it is this very drive to question, to look beyond the surface, to strive for a deeper understanding, that is the hallmark of our species. The holographic principle also invites us to reconsider our picture of science itself. Science is not a process of uncovering a single, fixed, and absolute truth. It is an evolving narrative, a story that we refine and rewrite with every new discovery. The idea that even our most fundamental concepts, like space and time, could be emergent, and perhaps even illusory, is a powerful testament to the open-ended and self-correcting nature of the scientific process. It teaches us that we must be prepared to question everything, to hold our most cherished theories with a degree of humility, and to be open to the possibility that the next great revolution in our understanding will come from a place we least expect. As we gaze into the deep mysteries of the universe, from the swirling, information-scrambling event horizons of black holes to the subtle, quantum fabric of space-time itself, the holographic principle stands as a beacon of what science can achieve when it dares to challenge its own most fundamental conventions. It is more than just a theory. It is a testament to the boundless creativity and the relentless curiosity of the human mind. And as we continue to explore the implications of this strange and beautiful idea, we are not just decoding the secrets of the cosmos, we are also, in a very real sense, decoding ourselves and our own mysterious and holographic place within the grand and perhaps illusory cosmic drama. The reality we perceive, with its solid objects, its linear flow of time, and its clear causal relationships, is like a beautifully woven and seemingly complete tapestry. But what if, on closer inspection, we find that the threads are not as tightly knit as they appear? What if we discover gaps, tears, and strange, unexplored patterns in this fabric we call existence? The journey into the heart of modern physics is a journey into this very realization. It is the discovery that our classical, common-sense picture of the world is a powerful but ultimately limited approximation of a much deeper, stranger, and more mysterious reality. And it is a journey that leads us to one of the most enigmatic questions of all: can we ever fully and completely decode the true nature of reality? The first and most profound challenge to our classical worldview comes from the quantum realm. The concept of an objective reality, the idea that the world exists with definite properties, independent of our observation of it, seems, at first glance, to be an obvious and necessary starting point for any scientific inquiry. A tree in the forest is a tree, whether we are there to see it or not. But quantum mechanics, with its strange logic of superposition and measurement, complicates this simple picture. The observer effect demonstrates that the very act of measuring a quantum system can alter its state. An electron does not have a definite position until we measure it. Before the measurement, it exists as a wave of probability. Our observation forces this wave to collapse into a single, definite location. It is as though the universe only paints the picture of reality once we decide to look at the canvas. This raises a deep and unsettling question: how much of what we perceive as real is a property of the world itself, and how much is a product of our interaction with it, a reflection of the questions we ask and the measurements we make? This inherent fuzziness of the quantum world is quantified by Heisenberg's uncertainty principle. At the most fundamental level, it is impossible to simultaneously know certain pairs of properties of a particle, like its position and its momentum, with perfect accuracy. The more precisely we know one, the less we can know about the other. This is not a limitation of our instruments. It is an intrinsic, built-in feature of nature. It is as if reality itself has a fundamental blurriness at its core, a limit to its own definiteness. This suggests that our quest for a complete and perfectly precise knowledge of the universe may be, in principle, an impossible one. This fundamental limit on our knowledge is not just a feature of the physical world, it is also a feature of the abstract, mathematical world we use to describe it. In 1931, the logician Kurt Gödel, in one of the most stunning intellectual achievements of the 20th century, proved his incompleteness theorems. These theorems show that in any sufficiently complex and consistent mathematical system, there will always be true statements that cannot be proven. Within the rules of that system, mathematics, the very language of science, the tool we use to build our theories of reality, is itself fundamentally and forever incomplete. This has profound implications. If even the abstract logical framework we use to understand the universe has inherent, unprovable truths, how can we ever hope to build a final, complete theory of everything? Gödel's work suggests that our knowledge will always be a work in progress, a system that can be made more complete only by introducing new and themselves unprovable axioms. The quest for an absolute final foundation for our knowledge is a logical impossibility. This inherent incompleteness of our theoretical frameworks is reflected in the ongoing and often contentious debates about the interpretation of quantum mechanics itself, the Copenhagen interpretation, the many worlds interpretation, Bohmian mechanics. Each of these offers a different and seemingly incompatible picture of the underlying reality of the quantum world. Each is a different and partial attempt to make sense of the same strange set of experimental results. The fact that, after a century of debate, there is still no consensus on which, if any, of these interpretations is correct is a powerful testament to the deep, and perhaps irreducible, mystery that lies at the heart of our most fundamental theory. But the limits of our knowledge are not just found in the bizarre world of the quantum or the abstract realm of mathematics. We also encounter them when we try to bridge the gap between the simple and the complex, between the microscopic and the macroscopic. This is the problem of emergence. The philosophy of reductionism, which has been a powerful and successful guiding principle in science, is the idea that we can understand a complex system by breaking it down into its simpler, constituent parts. We can understand the properties of a gas by understanding the behavior of its individual molecules. We can understand the chemistry of a protein by understanding the properties of its atoms. But this approach has its limits. There are many complex systems, from the flocking of birds to the functioning of a city, from the intricate folding of a protein to the emergence of consciousness in a brain, where the behavior of the whole seems to be more than just the sum of its parts. These systems exhibit emergent properties, novel and unpredictable behaviors that arise from the complex, nonlinear interactions of their many components. You cannot understand the beauty and complexity of a flock of starlings by studying a single starling in a cage. You cannot understand the subjective experience of consciousness by studying a single neuron under a microscope. The bridge between the microscopic laws of physics and the macroscopic, emergent realities of our world remains one of the great unsolved frontiers of science. The challenge of understanding complexity is not just a conceptual one, it is also a computational one. The idea that we could, in principle, simulate the entire universe on a powerful enough computer and thus uncover all its secrets is a tempting one. But the theory of computational complexity suggests that this may be an impossible dream. There are many systems in nature that are computationally irreducible. This means that there is no shortcut, no simpler calculation that can predict their future behavior. The only way to know what they will do is to let them do it, to run the simulation, step by step, in real time. The weather is a classic example. Even with the most powerful supercomputers, we cannot predict the weather with perfect accuracy beyond a few days, because the system is so complex and sensitive to initial conditions that small errors in our model are rapidly amplified. The universe itself may be the ultimate, computationally irreducible system. If this is the case, then a complete, predictive knowledge of its future is not just practically, but fundamentally impossible. The universe's story can only be told by living it. This inherent unpredictability is not just a matter of complexity. It is also a matter of the fundamental, probabilistic nature of the quantum world. As we have seen, the universe, at its core, is not deterministic. It is governed by the laws of probability. We can never predict with certainty when a single radioactive atom will decay. We can only know the probability of it decaying in a given time interval. If the universe itself operates on this probabilistic logic, then how can we ever hope to map out a single, definite reality? We are not chasing a single, hidden answer. We are trying to understand a vast and constantly unfolding landscape of possibility. All of these limits the uncertainty of the quantum world, the incompleteness of mathematics, the emergence of complexity, the irreducibility of computation, the probabilistic nature of reality bring us to a final and deeply philosophical question. Are these barriers epistemic, meaning they are a result of our own human limitations of knowledge and perception, or are they ontic, meaning they are a fundamental built-in feature of reality itself? Some philosophers in the instrumentalist tradition would argue that they are epistemic. Science is just a tool for making predictions, and its inability to provide a complete, certain, and final picture of reality is not a failure, but a reflection of its proper limited scope. Others, in the realist tradition, would argue that they are ontic. Our scientific theories, in their very structure, are telling us something deep and true about the nature of reality, that it is, in its essence, incomplete, uncertain, and open-ended. The quest to decode reality, then, is not a quest to find a final, single answer. It is a journey into an ever-deepening mystery. It is a process that requires not just intellectual rigor, but also a profound sense of humility, of wonder, and of acceptance of our own, and perhaps the universe's own, fundamental limitations. The tapestry of reality is not a finished work of art to be admired from a distance. It is a living, breathing, and constantly evolving fabric, and we are not just its observers, but an integral part of its intricate and beautiful weave. The strange and beautiful world of quantum mechanics, with its principles of superposition, entanglement, and measurement, does not just challenge our understanding of the physical world. It also offers a new and profound lens through which to view the deepest mystery of all the nature of our own consciousness. The dialogue between quantum physics and the study of the mind has long been a fertile, if often speculative, ground for inquiry, a place where the most advanced theories of science meet the most ancient questions of philosophy. Could it be that the way we perceive, think, and experience the world is fundamentally tied to the bizarre and counterintuitive logic of the quantum realm? At the very heart of quantum mechanics lies the concept of measurement, the process by which the ghostly probabilistic world of quantum superposition collapses into the definite, singular reality of our classical experience. As we have seen, the role of the observer in this process is deeply enigmatic. While most physicists would argue that a conscious mind is not necessary for the collapse to occur, the very structure of the theory, with its inherent distinction between the unobserved system and the observing apparatus, seems to hint at a special role for information and awareness. This has led some thinkers to propose a more direct link between the quantum and the mental. Could our own subjective experience of a single, coherent reality be a macroscopic reflection of this fundamental process of wave function collapse? Could each moment of conscious awareness be a moment of quantum decision, a point where the vast superpositional potential of our brain's neural activity is resolved into a single, definite thought, feeling, or perception? This brings us to the fascinating idea of cognitive superposition. In our everyday waking lives, our minds often seem to entertain multiple and sometimes contradictory possibilities at once. In a moment of indecision, we can feel the pull of different choices. We can mentally simulate different potential futures. A classical computational model of the brain might see this as a simple, sequential process of weighing different options, but a quantum perspective offers a more radical possibility. Could the brain, at some level, be operating like a quantum computer, capable of holding these different possibilities in a genuine physical state of superposition? Could our subjective experience of indecision be the conscious correlate of an uncollapsed superpositional state in the quantum activity of our neurons? This is a bold and highly speculative idea, but it is one that is being taken seriously by some researchers at the frontiers of neuroscience and quantum biology. The search for a physical quantum basis for consciousness is not just a philosophical fancy. It is a field of active, if controversial, scientific research. We know that biological systems are not just classical chemical machines. There is growing evidence that certain biological processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field, may be harnessing the strange and powerful effects of the quantum world. Could the human brain be another example of this quantum biology? The orchestrated objective reduction theory, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is the most well-known and specific model for how this might work. It posits that the fundamental units of quantum computation in the brain are not the neurons themselves, but the microtubules, the tiny cylindrical protein structures that form the cytoskeleton of our cells. Penrose and Hameroff argue that the quantum states within these microtubules can exist in a superposition of different configurations, and that these superpositions are the physical basis of our pre-conscious processing. Consciousness in this model arises at the moment of objective reduction, a spontaneous collapse of this quantum superposition that is triggered by a fundamental gravitational instability at the Planck scale. Each of these collapse events, happening many times a second, corresponds to a single, discrete moment of conscious experience. The OR theory is highly speculative and faces a number of significant scientific challenges, particularly the question of how a fragile quantum state could be maintained in the warm, wet, and noisy environment of the brain. But it is a testament to the growing interest in exploring the potential quantum nature of the mind. The observer effect in quantum mechanics, the idea that the act of observation can influence the state of a physical system, also finds a powerful metaphorical, and perhaps even literal, resonance in our understanding of consciousness. Our attention, our awareness, is not a passive spotlight that simply illuminates a pre-existing mental landscape. It is an active, creative force that shapes and transforms our inner world. When we bring a quality of mindful, non-judgmental awareness to a difficult emotion, like fear or anger, we can often feel its energetic quality shift and change. The act of observing it, without being identified with it, seems to collapse its power, to transform it from a solid, overwhelming reality into a more fluid and manageable experience. This is the basis of many contemplative and therapeutic practices. And it is an experience that hints at the possibility that our consciousness is not just a product of the brain, but is a fundamental, causal agent in the brain, a force that can influence the very physical processes that give rise to it. The bridge between the quantum and the classical, the strange and the familiar, may be found in the process of decoherence. As we have seen, decoherence is what explains why we do not experience the world as a constant, blurry superposition. A quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence. The information about its superposition is spread out into the surrounding world, and for all practical purposes, the system behaves classically. This principle is what safeguards our classical, everyday reality from the bizarre, underlying quantum weirdness. But it also offers a new way to think about the nature of perception itself. Our sensory organs, our eyes, our ears, our skin are macroscopic measuring devices. They are constantly interacting with and entangling with the quantum systems of the external world. The act of perception is a process of decoherence. When a photon from a distant star hits a retinal molecule in your eye, it triggers a cascade of classical chemical events. The quantum information of the photon's superpositional state is effectively measured and collapsed into a definite, classical signal that is then processed by your brain. Our classical perception of the world is, in this sense, a consequence of the constant entropic loss of quantum information. We see a definite, classical world because our very act of seeing is a process that destroys the underlying quantum reality. This leads to a profound and humbling conclusion. The reality we experience is not the full reality. It is a collapsed reality, a simplified and likely very partial representation of a much richer and far stranger quantum world. The discussion of consciousness and quantum mechanics inevitably leads to the age-old debate about free will. A classical, deterministic universe, governed by the clockwork laws of Newton, seems to leave no room for genuine freedom. Our choices would be nothing more than the inevitable outcome of a long chain of prior causes and effects. But the quantum world, with its inherent, irreducible randomness, seems to open a door. The collapse of the wave function is a probabilistic event. The outcome is not predetermined. Some have argued that this quantum indeterminacy could be the physical basis for our experience of free will. Perhaps our choices are not the result of a deterministic, computational process in our brains, but are, at some level, the result of the amplification of these random quantum events. This is a controversial idea, as it seems to equate free will with pure chance, which is not what we usually mean by freedom. But a more sophisticated version of this idea suggests that our conscious mind may be able to influence the probabilities of these quantum events, to steer the collapse of the wave function in a way that is consistent with our intentions, without violating the statistical laws of quantum mechanics. This is a deep and difficult problem, and one that is far from being solved. But the dialogue between quantum mechanics and consciousness, for all its speculative nature, is a powerful and important one. It is a dialogue that is pushing the boundaries of both science and philosophy. It is forcing us to question our most basic assumptions about the nature of reality, of the mind, and of the relationship between the two. It is a reminder that the universe is far more intricate, far more interconnected, and far more wondrous than our classical intuition can ever reveal. And it is an invitation to explore the deep and as yet uncharted territory where the mysteries of the outer cosmos meet the mysteries of our own inner world. The universe is brimming with information. It is encoded in the complex, swirling patterns of a galaxy, in the precise, orbital dance of a planetary system, in the fiery thermonuclear heart of a star, in the elegant double helix structure of a DNA molecule, and in the strange probabilistic wave function of a single subatomic particle. From the grandest cosmic scales to the most infinitesimal quantum ones, information is the thread that weaves the fabric of reality. But what happens to this information over the long and often violent course of cosmic history? Is it preserved forever, a perfect, indelible record of all that has ever been? Or can it be lost, erased, destroyed in the great entropic wash of time? This is one of the most fundamental and deeply debated questions in all of modern physics. A question that touches on the nature of time, of entropy, of black holes, and of the very laws of the universe itself. To understand the fate of information, we must first understand its foundations in both classical and quantum physics. In the classical world, information is, in principle, always preserved. This is a direct consequence of the deterministic nature of classical laws. If you know the precise state of a closed system at one moment in time, the position and velocity of every particle, then the laws of physics allow you to, in principle, calculate its state at any other time, both in the future and in the past. Information is never lost. It is just rearranged. But the quantum world, as we have seen, operates on a different logic. The process of decoherence seems to imply a fundamental loss of information. When a quantum system interacts with its environment, the information about its delicate superpositional state is rapidly spread out and dissipated, becoming, for all practical purposes, irretrievably lost. This is why our macroscopic world appears to be classical, even though it is built from quantum components. The quantum weirdness is constantly being washed away by the entropic tide of environmental interaction. Understanding and controlling this process of decoherence is one of the central challenges in the development of practical quantum technologies. To build a powerful quantum computer, we must find ways to isolate our qubits from their environment, to shield them from the relentless process of decoherence, long enough for them to perform their complex calculations. The quest to build a quantum computer is, in a very real sense, a battle against the informational entropy of the universe. The deep and intimate connection between information and entropy is a cornerstone of modern physics, a connection that is most beautifully illustrated by the laws of thermodynamics. The second law of thermodynamics, as we have seen, states that the entropy, or disorder, of a closed system always increases over time. This is the law that gives time its arrow, but information can be seen as the very opposite of entropy. It is a measure of order, of structure, of reduced uncertainty. When we gain information about a system, we are, in a sense, locally reducing its entropy. This is the paradox of Maxwell's demon, the hypothetical being who could seemingly violate the second law by sorting hot and cold molecules. The resolution to the paradox lies in the realization that the demon itself, in the process of acquiring and processing information, must generate at least as much entropy as it reduces, thus preserving the overall validity of the second law. This connection was made even more explicit by Landauer's principle, which states that the erasure of information is an irreversible, entropy-increasing process. To erase a single bit of information from a computer's memory, you must release a minimum amount of heat into the environment. Information is not an abstract, disembodied entity. It has a real physical cost. It is tied, by the fundamental laws of nature, to the world of energy and entropy. On the grand cosmic scale, the universe itself can be seen as a vast and ancient repository of information. The cosmic microwave background, the faint afterglow of the Big Bang, is not just a uniform glow. Its tiny temperature fluctuations are a snapshot of the primordial information, the quantum seeds from which all the structure in the universe grew, the large-scale distribution of galaxies, the intricate chemical composition of the stars, the complex geological history of a planet. All of these are records, archives of the universe's long and complex evolutionary story. But what is the ultimate fate of all this cosmic information? Does the universe have a finite memory? The accelerating expansion of the cosmos, driven by dark energy, raises a profound and unsettling possibility. If the universe continues to expand at an ever-increasing rate, then the information contained in distant galaxies will eventually be stretched and redshifted into oblivion, lost forever beyond our cosmic event horizon. The observable universe will become an increasingly barren and information-poor place. And the enigmas of dark matter and dark energy add another layer of mystery. Does dark matter, which makes up the vast majority of the matter in the universe, play a role in storing or processing information? Or is it an informationally inert, passive background? And what is the informational nature of dark energy itself? Is it a simple, constant energy of the vacuum, or is it a dynamic, information-rich field that is evolving over time? These are some of the most profound and challenging questions in all of cosmology. Perhaps the most intriguing and challenging intersection between information and the cosmos lies in the nature of gravity itself. For decades, the quest to unify general relativity and quantum mechanics has been the holy grail of theoretical physics, and in recent years, a new and powerful idea has emerged that gravity itself may not be a fundamental force, but an emergent phenomenon, something that arises from the deeper quantum informational structure of the universe. The idea is that the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space. The curvature that we perceive as gravity is a macroscopic manifestation of the intricate web of quantum correlations between the fundamental constituents of reality. In this view, information is not just in the universe is information. This is a radical and beautiful vision, and it is one that is supported by the holographic principle. The idea that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This principle, which first arose from the study of the thermodynamics of black holes, suggests that our familiar three-dimensional world may be a kind of cosmic hologram, a projection of a more fundamental, two-dimensional informational reality. This would have profound implications for the black hole information paradox. If the information about the matter that falls into a black hole is encoded on its two-dimensional event horizon, then it is never truly lost to the universe. As the black hole evaporates, this information could be subtly and complexly imprinted onto the outgoing Hawking radiation, thus preserving the fundamental principles of quantum mechanics. And what of the ultimate fate of the universe in this informational picture? If the universe is destined for a heat death, a state of maximum entropy where all energy is evenly distributed and no useful work can be done, would this also be a state of information death? Would all the complex ordered information that has been created over billions of years of cosmic and biological evolution be lost in a final, uniform sea of thermal noise, or could information persist? Even in this seemingly final state, some speculative theories suggest that even in a heat death scenario, the quantum fluctuations of the vacuum would continue, and that over immense, almost unimaginable timescales, new, ordered structures could spontaneously fluctuate into existence. The universe could, in a sense, be reborn from its own informational ashes. The study of information in physics is a rapidly evolving and incredibly exciting field. It is a field that is blurring the lines between physics, computer science, and philosophy. It is forcing us to rethink our most basic concepts of reality, of space, of time, of causality. And it is a field that is driven by a single, powerful, and unifying idea that to understand the universe, we must understand its information. The cosmos is not just a collection of matter and energy. It is a story, a message, a vast and ongoing computation. And in learning to read this cosmic code, we are not just deciphering the secrets of the universe. We are also, in a very real sense, discovering the deep informational nature of ourselves. The future of humanity has always been inextricably linked to our ability to create, to process, and to transmit information. From the invention of language and writing to the development of the printing press and the Internet, every major leap in our information technology has been a major leap in our civilization. And today, we stand on the cusp of a new and potentially even more transformative revolution. A revolution that is being driven by the strange and powerful logic of the quantum world. The future of information is a story of two converging technologies, artificial intelligence and the quantum internet. And their combination holds the promise to redefine not just our technology, but the very fabric of human existence. Artificial intelligence, once the stuff of science fiction, is now a ubiquitous part of our everyday lives. It is in the virtual assistants that organize our schedules, in the recommendation algorithms that shape our cultural tastes, in the sophisticated systems that help doctors to diagnose disease and scientists to analyze vast and complex data sets. The power of modern AI lies in its ability to learn from data, to recognize patterns, and to make predictions with a speed and an accuracy that can far surpass human capabilities. But for all its power, our current AI is still limited. It is a form of narrow AI, a system that is incredibly good at performing specific, well-defined tasks, but that lacks the general, flexible, and creative intelligence of a human mind. The story of AI is still in its early chapters, and the next, and perhaps most exciting, chapter may be written in the language of quantum information. The concept of quantum information, as we have seen, is a radical departure from the classical binary logic of our current computers. A quantum computer, by harnessing the principles of superposition and entanglement, can process information in a fundamentally new and more powerful way. It can explore a vast, multidimensional computational space simultaneously, giving it the potential to solve certain classes of problems that are, for all practical purposes, unsolvable for any classical machine. Imagine an AI system that is not limited by the linear, step-by-step logic of a classical computer, but can think in the rich, probabilistic, and superpositional language of the quantum world. This is the promise of quantum AI. Why? A quantum AI could, in principle, analyze a vast and complex landscape of possibilities in an instant, allowing it to solve complex optimization problems, to design new materials with novel properties, or to discover new drugs by simulating the quantum behavior of molecules with perfect fidelity. It could be an engine of scientific discovery and technological innovation of unprecedented power. But the quantum revolution is not just about computation, it is also about communication. And this is where the second part of our story begins, the development of the quantum internet. A classical internet transmits information as bits of data encoded in pulses of light or electrical signals. A quantum internet would transmit information as qubits encoded in the quantum states of single particles, like photons, and its primary, and most revolutionary, feature would be its inherent and perfect security. As we have seen, the principles of quantum mechanics, like the no-cloning theorem and the observer effect, make it impossible to intercept or copy a quantum communication without being detected. A quantum internet would be a truly unhackable network, a development that could revolutionize every industry that relies on the secure transmission of data, from finance and government to healthcare and defense. But the potential of a quantum internet extends far beyond secure communication. It would also be a network that can transmit entanglement. It would allow us to create and distribute these strange, non-local quantum connections between distant quantum computers, linking them together into a single, global quantum computational network. This would allow us to tackle problems that are too large and complex for even a single, powerful quantum computer. It would be a new kind of global collaboration, a new way of harnessing the collective, computational power of the quantum world. Now, let us think even bigger, even more speculatively. What is the ultimate, long-term potential of this quantum information revolution? The astrophysicist Nikolai Kardashev famously proposed a scale for categorizing hypothetical and advanced extraterrestrial civilizations based on their ability to harness energy. A Type 1 civilization is one that can harness all the energy of its home planet. A Type 2 can harness all the energy of its host star, and a Type 3 can command the power of its entire galaxy. We can imagine a similar scale for the mastery of information. What if a future advanced civilization could learn to harness and process information on a cosmic scale? What if they could build a galactic-scale quantum internet, a network that connects not just computers, but planets, stars, and perhaps even different regions of space-time? This is a provocative and highly speculative notion, but it is a logical, long-term extension of the technological trajectory we are on. If information is the currency of intelligence, then the ability to manage information on a cosmic scale could allow a civilization to unlock secrets of the universe that we can't even begin to comprehend. Could this be an evolutionary milestone for advanced life? Could the mastery of quantum information be the key to reaching a new and higher level of cosmic consciousness? Naturally, these bold and futuristic ideas spark a host of profound ethical and philosophical questions. The development of a true general artificial intelligence, whether classical or quantum, would be a watershed moment in the history of life on Earth. How would we ensure that such an intelligence is aligned with human values? How would we prevent it from being misused? What would be our own role and purpose in a world where we are no longer the most intelligent beings on the planet? These are not just technical challenges, they are deep, societal, and existential ones. Similarly, the development of a global quantum internet, while offering the promise of perfect security, also raises questions about privacy, surveillance, and control. Who would own and control this new fundamental layer of our information infrastructure? How would we ensure that its benefits are distributed equitably and that it does not become a tool for creating an even wider gap between the haves and the have-nots of the information age? The democratization of these powerful new technologies will be one of the most critical challenges of the coming century. And of course, there are the skeptics. Some argue that the warm, wet, and noisy environment of a biological brain is simply not conducive to the kind of delicate, coherent quantum processes that would be needed for a quantum mind. Others argue that even a powerful quantum AI would never be able to replicate the true, subjective experience of human consciousness, with all its intuition, its creativity, its capacity for love and sorrow. These are valid and important critiques, and the debate is far from settled. But even if the most ambitious claims for quantum consciousness and AGI do not come to pass, the journey itself is transforming our world. The promise of quantum information is reshaping our understanding of artificial intelligence. The development of the quantum internet is redefining the future of communication. And the futuristic vision of a civilization that can harness information on a cosmic scale is providing a new and powerful lens through which to view our own long-term evolutionary future. The future of information is not just about faster computers or more secure networks. It is about redefining what it means to live in an interconnected, intelligent, and information-rich world. It is about uncovering new truths, not just about the universe, but about ourselves. It is about understanding what a civilization can achieve when its technological innovation is guided by its deepest imaginative and ethical aspirations. As we conclude this exploration, the question we are left with is not, what is the future of information? But rather, How will we choose to shape our future with the new and powerful forms of information that we are now, for the first time in history, beginning to create? The possibilities are infinite, the questions are profound, and the answers, for now, are waiting for us in the strange, beautiful, and endlessly creative quantum unknown.